Hey, welcome back, everybody. This is Jonathan Templin at Clemson University, and I'm here to talk to you about estimation methods. But before I start, let's talk about why. Estimation methods are kind of a technical topic, and oftentimes we kind of skip over those quickly in class. However, there's a kind of a big gap between the types of methods you use when you're using linear models, which is often least squares based, and more advanced models like mixed, multi-level, structural equation, etc. The latter, the more advanced models, often run with estimation methods that are called, fall under the heading of maximum likelihood or Bayesian. And the types of information and details you get out of the machine when you run your models are different. So, part of the reason I'm describing this to you in a lecture is to get you prepared for what we're about to see with more complex models and estimation methods. But it's also because, particularly likelihood based, maximum likelihood based methods, how we evaluate significance of parameters and model comparisons also changes. But many things look the same as you saw before. So my goal in this lecture is to give you a basic overview of how things are estimated and some mathematical statistics that underlie those, because this will come up over and over again as we move. I've often found that students experience quite a gap between least square space methods and maximum likelihood based methods when they move on from the basic linear models. So let's get into it. We're going to begin today talking about the building blocks of how models and methods work, in particular mathematical statistics. And in the term mathematical statistics is really the idea that of doing the underlying mathematics that follows under our statistics methods. Basically, it's like doing statistics with no data, describing models based on their properties and the mathematical form. So to do so, we're going to have a lot of definitions. We're going to define random variables, different types of random variables. We'll cover a little bit about univariate distributions, such as the normal distribution or Gaussian. We'll talk about other popular, which I think is kind of a super popular distribution. Other well-known and commonly used univariate distributions. We'll get into describing different types of distributions. So we may have a marginal distribution or a conditional distribution or a joint distribution. And we'll talk a little bit about properties of distributions or linear combinations that we really need to think about when we get into more complex things, in particular means, variances, and what we call the algebra of expectations. And we're going to do this to really talk about linear combinations of random variables. For instance, in a linear model with interactions, you may want to form simple slopes. You might want to find conditional slopes for different interacting variables. And how you look at those, whether you look at their point estimates would be the mean, how you look at their standard errors comes to the algebra expectations for variances, and you'll have to understand covariance involved in that as well too. So we'll put this together and we'll end up with a finished product of how the general linear model fits within statistics. So how it applies with the normal distribution, what are the statistical assumptions of the general linear model, and how to assess these assumptions. Then we'll get into maximum likelihood and least squares, comparing and contrasting them. We'll describe the basics of maximum likelihood estimation, which is the engine that really drives most modern statistical methods. We'll also have additional information from maximum likelihood estimators, such as likelihood ratio tests, wall tests, and information criteria. Again, these are the methods that we use in maximum likelihood to evaluate the statistical significance of a model, of a set of one or more parameters, or to compare and contrast two different competing models to see which ones appears to be more effective for your data. Finally, we'll talk about maximum likelihood estimation in general linear models, and I'll introduce to you a couple different R packages, NLME, which is nonlinear mixed effects, and LME, the linear mixed effects packages in R. And we'll also talk a little bit about the Levon package in R, which uses maximum likelihood for path analysis and structural equation modeling. Finally, we'll wrap up with an introduction to Bayesian estimation. We'll talk about Bayesian statistics. In short, Bayesian takes the likelihood from a maximum likelihood model and applies prior distributions on parameters. And prior distributions are ways that we characterize prior beliefs, either that's subjective, directly from our own thought about whether a parameter value might be, or from previous studies where we have empirical data on what previous parameters might be. So we'll describe what Bayesian statistics is, what it does, how and why people use it. And we'll also cover a little bit of Markov chain Monte Carlo, or MCMC estimation, which is how often we use the estimation method that we use to implement Bayesian statistical methods. All right, let's dive in. Okay, let's cover random variables and statistical distributions. Let's define what a random variable happens to be. First of all, random. Situations in which the outcome, a certainty of the outcome, is unknown and is in part due to chance. Think of flipping a coin. If the outcome were the side of the coin that landed heads up or tails up, we know that when we flip the coin, we don't necessarily understand what would happen, so we call that chance. A variable is a value that may change given the scope of a problem or set of operations, right? Contrast to a variable, we probably don't need a whole lot of that, but just think about a variable is something that is a piece of data that has multiple values. It's not a constant. When we put the two together, we get random variable, which is a variable whose outcome depends on chance itself. Right? So possible values might represent the possible outcomes of a yet to be performed experiment. I will say experiment is sort of the classical word that we say this. This could be an observational study as well too. Think of people walking into a convenience store that has that height strip marking on the wall. And we're talking about how tall each person is as they walk through the door. So in that case, the height itself may be a random variable. And as we know, just clearly by lived experience, people vary in their height. That would be a random variable. And it has nothing to do with an experiment. In this case, the word experiment just applies to the observation that we're doing. So what we're going to do mathematically is denote a random variable with a lowercase x, like this, as we go forward. Now, there are different types of random variables. Random variables can be continuous, discrete, or mixture. And what defines their type is really given by the set of values they can take. So continuous random variables are things like height, or the outcome or dependent variable in a general linear model. Really, the idea behind a continuous random variable is if we had a measurement instrument that was so precise that we can get infinitesimally small differences, you would see that height really is on a continuum. Like, so you can think of height as going from 0 up to some number. Of course, there is an upper bound to height given each species. So we can get deeper down a philosophical rabbit hole here. But you can think of in between that, think of the range of height. If we had a really precise like height strip on that door of the convenience store, what we would be able to tell is that people may be, let's say 72 inches tall, or there might be a person comes in 72.0002 inches tall. But the bigger picture is the continuous nature of that random variable means that there's no discrete steps in height. Height can literally be any number that goes from 0 up to where we would call the maximum value possible, the tallest person who we've ever recorded, for instance. So that contrasts with discrete random variables, sometimes called categorical. Discrete random variables are things that are categories, where there is no continuum at all. Now, there can be an ordering, right? You can talk about place a person achieved in a race. But another version of a discrete random variable could be, let's say, a 0-1 variable, whether or not a person took a nap today, right? If a person took a nap, we'll give a 1. If a person did not, we'll give a 0. Right? Nap sounds pretty good right about now for me. But leaving that aside, you can tell the difference between a continuous and a discrete random variable in this example is that there's no half naps. Either you fell asleep or you did not. Even if the nap lasted all of a minute, you fell asleep or you did not. I hope you're not going to nap while I keep talking about this, though. Finally, we could have random variables that are a mixture of both continuous and discrete, right? So for instance, we might have an experiment we're actually running where we want someone's response. We prompt them with a question or some type of stimulus on a screen, and they have to reply with an answer between 0 and 45 seconds. And if they reply with an answer within 45 seconds, we actually put down the amount of time it took them to get that answer. And if they didn't, we put a 0, right? Clearly, response time can't be 0 because you can't instantaneously respond to a prompt. There has to be at least a millisecond that goes in between there. So 0 really is not in the range of time for this, but 0 might represent somebody who's far out of bounds, right? Beyond 45 seconds. As my son might say, they are AFK, away from keyboard. So we don't want to record that after 45 seconds because perhaps that would indicate that somebody has just stopped paying attention to the task at all. So that would be a mixture. But this is important. The type of random variable is important because that sets up the type of distribution. So continuous random variables have continuous distributions. Discrete random variables have discrete distributions, and mixtures have sort of a combination of both. So random variables themselves are described by their distributions. And those distributions themselves, if you think of like the bell curve, that is a distribution. It actually has a name. It's called the probability density function, or PDF, right? A probability density function is usually applied to continuous random variables. That term usually falls under continuous, as opposed to a probability mass function that would go with a discrete random variable. So if we're talking about the probability or the proportion of people who took a nap today, you would have a 0 and you'd have a bar that has what proportion that is, and you have a 1. So a PDF or a PMF is a mathematical function that gives a rough picture of the distribution from which a variable is drawn. And there's a mathematical equation that underlies each PDF or PMF. So the type of random variables dictates the name and the nature, right? Continuous random variables, we use the probability density function, a PDF. And so here, let's see if I can draw a bell curve. Not my best work, but hopefully that'll work for today. So we have X, that's our random variable. Maybe this is, height. Turns out this PDF, the area, there's a couple features of it that are of note. The area underneath the curve has to integrate to 1. The reason for that is that this is sort of a probability measure, and probability is defined between 0 and 1. You can't have a probability less than 0, a probability more than 1. When I say probability measure, I'm really talking about what's underneath, or a range of variables, right? So if you took an X right here, the area to the left of that line would represent all the probability someone is below that point, right? So that's the probability measure I'm talking about. But note, I'm not talking about the height of the function. Right, so let's take a look. The height of the function here, this dot, that is a likelihood value, or a relative frequency is what we might call it. Right? It's the relative likelihood of observing that value of X itself. Now, it's not probability because if you think about this shape, to get this to integrate to 1, the shape itself may take, depending on the distribution, it may have a very narrow range. We might find a continuous distribution that looks like this right here. So the value of f of X, the value that returns from the PDF, is not a probability, but it's a relative likelihood. So we can use it to compare values. All right. So imagine if we have an X here in the center of the distribution, and we want to compare that with an X here at the very tail of the distribution. What we would say is the value that has the higher f of X, the higher relative likelihood, is more likely to have been observed if this were the distribution that we're coming from. All right, let's compare that with discrete random variables. In discrete random variables, X might take a 0 or a 1. Let's go with our did you take a nap today example. I don't know what the base rate is for people taking a nap. I know that I don't take many naps. So let's put 0 up here. Let's put 1 down here. Let's try that. And this is still f of X. Now, a discrete random variable has something called a probability mass function, or PMF. I will say that this is more of a technical thing. If you just say, oh, the distribution function or the PDF, you can use that for either. Most people will understand it. But if you want to get into the weeds, probability mass function. Now, here, the key is the sum of these two values has to sum to 1, right? So the sum of 0, the height of 0, and the sum of 1. So this actually makes these actual probabilities. So the y-axis represents the probability, the height of this bar represents the probability that someone did not take a nap. And the height of the lower bar is the probability that someone did take a nap. So the big difference in these distribution function is that for continuous variables, the height does not represent a probability. It's it's like a relative frequency. Sometimes we call it a likelihood. And for discrete variables, that height really does represent probability. So there are a couple other key terms that we have to define when it comes to variables. The sample space is the set of all values that a random variable can possibly take. Now, in this case, we're in mathematical statistics land. So just disregard data for a moment. Just think about it this way. If we say X follows a normal distribution and we go look up the normal distribution information in a technical source, or heck, we just look up normal distribution on Wikipedia, we'll see that x can range between negative infinity and positive infinity, meaning all real numbers. That means that is the sample space, or sometimes called the support of x. That is where the distribution is valid. Basically, if you go back to my drawing, this bell curve extends to negative infinity at the left-hand side, and if you go up here, it's positive infinity up there. So the sample space for a random variable representing the outcome of a coin flip may be heads or tails. Now you can tell x, normal distribution, all real numbers, that's a continuous distribution. Flip of a coin, that's a discrete distribution. So that could either be heads or tails. Now some of you might say, what about the edge? Let's just disregard the edge for right now. More importantly, when we have a discrete distribution, we often put the set of values into the set notation where we see braces on either side, and the discrete values that the coin, the outcome could be in the center, with separated by commas. Likewise, if we try this with the roll of a die, a six-sided die, and we talk about the number of dots facing up once we roll the die, the sample space for that random variable would be the numbers 1, 2, 3, 4, 5, 6. Again, discrete values are whole like integer numbers themselves. I will note that these discrete values in discrete distributions, these are bounded discrete distributions, meaning there's a finite set of these numbers, 1 through 6 versus or heads or tails. We could come up with a count variable. A count variable is slightly different in that it has a fixed zero. Let's talk about number of naps someone took in the past 30 days, right? So, and now in this case, you can think of a nap as being any discrete event where you fall asleep and then wake up again. So you could take multiple naps a day. If we count the number of times a person napped over 30 days, you can have a zero. Somebody took no naps, or you have an upper point that is not set, right? It wouldn't be 6. We wouldn't know what the upper point is. And in a mathematical sense, that upper point could be infinite. Now, we know practically speaking, most people cannot take infinite naps, although that would be kind of an interesting thing if you could. I bet there'd be people that would sign up for that. But I digress. Anyway, discrete distributions can have a closed set or can have sort of an infinite set as well too. Now, why I'm talking about all this is because if you have continuous data and you have an outcome like y, like if we're trying to predict, let's say, the height of people coming in through the convenience store, that linear model for y, we could use a linear model for y if y is what we call plausibly continuous. It assumes a continuous outcome, a continuous space. But if we were to predict whether or not a person would take a nap based on events of their day, if we were to literally just look at, yes, they took a nap, no, they did not, a 0, 1 variable, that would not really work well in a linear model when we assume continuous data. So what we end up doing is changing the distribution that we assume in the model, thereby making it what's called a generalized linear model or generalized model. And why I'm talking about all this is because when we get to generalized linear models, the trick is to pick a distribution with a sample space that matches the range of values obtainable by data, right? So for height, a normal distribution might fit that pretty well. Whereas for number of naps in 30 days, you would need a distribution that would basically have a 0 lower bound and potentially an infinite number for the upper bound. Or if you were talking about the probability, let's say someone took a nap on a given day, yes or no, did they take any naps on a day? The 0, 1 variable, that's another distribution, something we would call Bernoulli. And we'll talk about that as we go forward too. All right, so we use the statistical models themselves make distributional assumptions based on various parameters and or parts of data. In sense of parameters, we're talking about that, like in a linear model, the regression coefficients themselves, or parts of data. That might be the outcome variable. It might be some of the values of the predictors. And these assumptions that are made govern how the models are estimated, how the inferences are made, basically what does it mean, what is statistical significant, and even how missing data might be imputed, right? So knowing about distributions is incredibly important because each of those topics that we will cover depends upon the type of distribution that you're using. And if you have a mismatch, right? Let's imagine We wanted to collect the number of times, let's just say whether or not a person took a nap or not on a given day, 0 or 1. If we use a continuous distribution for that, we're not going to have an accurate representation if we were to impute or fill in data. We would have to find a distribution that would result in a 0 or a 1. Right? And here's the thing, depending on the size of the mismatch, there could be substantial inaccuracies in your model if you don't match the data to the type of distribution you assume. Now, we're going to show that in just a little bit as well, too. So why I'm talking about this is because it may be helpful to check distributional assumptions prior to or during your statistical analyses. You need to make sure that the data match the model as you go forward. Now let's talk about continuous univariate distributions. Continuous univariate distributions are distributions where the sample space or support is somehow a continuum. And we're going to talk about how these distributions work and look when we plot them. We're going to give you 3 distributions. It's just me talking. I am going to give you 3 distributions to talk about today. The uniform distribution, a normal distribution, that's like the bell curve, and something called a chi-square distribution. And you may have heard chi-square before from statistics. That is definitely not a coincidence. Excuse me. Yeah, not a coincidence. I got that right. Anyway, each of these are going to be described by a set of parameters. So when you have a distribution on the theoretical side, the shape and range of that distribution follows a mathematical form. We talked about the probability density function. And within the probability density function, there are a set of parameters that govern the shape of it. We will later see these parameters themselves are what give us the inferences when we analyze data. Right? So what we often do is put constraints on those parameters based on hypothesized effects in our data. But we'll get into that. It's a little bit more technical right now. For now, I just want you to think there's a distribution, like a uniform. You may not have seen one of those before. It's governed by a set of a distribution, a PDF, right? We're in continuous univariate distributions. That's probability density function. And each PDF has a set of parameters. So in the uniform distribution is a nice distribution to get started because it shows us a little bit about how continuous distributions work. So let's first talk about the sample space. For this continuous random variable x, it ranges from the values a and to b, not inclusive of the endpoint. So we have these little curved parentheses putting a and b in there. And this is not a set. This is not meaning it takes a and b discretely. It just ranges from a to b. And if you look at the plot down here, a is the lower bound and b is the upper bound. So the PDF for the uniform distribution is 1 divided by the upper bound b minus the lower bound a. It makes a box. It's a flat line. Right? So what we would say is there are two parameters in this distribution, a and b, and we may denote a uniform distribution with the terminology here at the bottom of the page, where the random variable x, this little tilde or squiggle here, we often say is independently and identically distributed as, or I just say x follows. The distribution with u refers to uniform, and in the parentheses, we stick the parameters a and b. So let's think a little bit more about what this means. Remember how we said the height of a PDF represents the relative likelihood of observing a value. So in the uniform PDF, if we have a value here and a value here, what we see is they're both equally likely. In fact, all values between a and b are equally likely in the uniform. And then you see below here, this is actually 0. If you extend beyond the range of a and b, the PDF is 0. There's no chance. So really, this is just a nice, simple box for how we make things work. So let's try a few values and see how this works a little bit more. Right? So if we plug in x of 0.5, you see in the PDF of the uniform, x does not appear on the right-hand side. Right? It's just this flat line right here. Further, the area of this, if you think about the area of a rectangle, it's the length times the width, right? Well, here, what is the length? It's b minus a. Right? So the height of it has to integrate to 1. So that's why 1 over b minus a happens to be its height. So b minus a, its length, times 1 minus b minus a, its height, gives us an area of 1 in this box. So we don't have to use calculus or integration to make that happen. But again, if we were to plug in values of x, first of all, there's no place to put x in the PDF. So it doesn't really matter where x is, so long as it's between 0 and 1. And a 0.5 and a 0.75 are both between 0 and 1. Right? If we have an upper bound of 1, a lower bound of 0, and you'll see the relative likelihood for each, the result of the PDF, is 1 for each of those, indicating both are relatively likely. Now, if we get a little bit further down here, let's imagine we have a uniform ranging between 0 and 20, and we say, what's the relative likelihood or the likelihood of a 15? It's 0.05. Right? Similarly, if we have a different uniform between 10 and 20, and we plug in a 15, its relative likelihood is 0.1. And you might say, oh, hey, this is more likely than that. But remember, this is a completely this distribution has different parameters. So it's not really easy to compare and contrast across the two different distributions. So once again, the uniform has the feature that all values of x are equally likely across the sample space of the distribution. So you don't see x in the PDF. Turns out the mean of the uniform distribution is 1/2 a plus b. Right? It's actually right there in the middle. So much so that if you were looking at this box, the middle point, the mean, if we were to try to balance a box on it, it would be the fulcrum, right? The point where balance happens. Similarly, the variance is 1/12 b minus a squared. You might be like, what is that all about? Yep. Well, turns out these numbers are derived using calculus and the algebra of expectations, which we'll talk a little bit about later. We will never derive things with calculus in this class, but just understanding where they come from is important. Let's move on to the normal distribution or the Gaussian distribution, depending on what you prefer, Gauss being the person who is thought to have discovered the distribution. For a continuous random variable x that ranges from negative infinity to infinity, so that is the sample space, the univariate normal distribution function, or PDF, is given by this equation right here. Right? This exp, that is sometimes referred to as Euler's constant, or e raised to a power. E raised to the first power is approximately 2.71, and its inverse is the natural logarithm. It just so happens that we just denote this with exp. So you think about all this term here in the parentheses is actually an exponent. So there are two parameters in the normal distribution, the mean, mu, which you see here, and which shows up in the mean spot here, and the variance is sigma squared x, which shows up in the exponent and shows up in this part in the front. Now, sometimes because x does not appear in this front section, sometimes refer to this as a normalizing constant, meaning the random variable isn't there. So for everybody, it's the same so long as we know what the variance happens to be. Furthermore, we also describe these two parameters potentially as being sufficient statistics. I won't describe, that's a little bit even more technical than we need to get for this, but you just know that they contain all the information about the distribution, right? So if you believe in that your data follow a normal distribution, what you're saying is there's no skewness to your distribution, it's symmetric. There's no kurtosis, right? This is the peakness, how peaked or how flat that distribution happens to be. These actually, there is peakness, but it's a fixed value, but there is no skewness. Okay? So what you're saying is you can characterize the shape of your data entirely with two parameters, where the center happens to be, the mean, and how much spread there is, the variance. Now the standard notation again is x tilde, or is identically and independently distributed as a normal distribution with a mean and variance put in parentheses, or you can just say x follows the normal distribution with a mean mu x and a variance sigma squared x. Now, the normal distribution is everywhere. That's probably why it gets its name normal. Although it sort of implies if a distribution is not normal, that's almost like a clinical judgment on the distribution. When in this case, it just means normal shows up everywhere because it turns out it has some really easy properties to work with. Like, for instance, linear combinations of random variables following normal distributions also follow a normal distribution. So you have x that's it's normal, and you have y that's normal. If you add them together, their sum is also normal. We actually are going to use that in figuring out linear combinations of parameters and how their significance values or the distributions happen to work. Here's a couple plots from Wikipedia of normal distributions, and you can tell the difference for each. So for instance, the red line, this is a normal distribution with a mean of 0, variance of 1. Sometimes we call this a standard normal distribution, meaning basically these values are like z-scores, right? Mean of 0, variance or standard deviation 1. If we shrink that standard deviation, the distribution becomes more peaked, which is that blue line right there. Still the same center. The mean is at the center of the distribution. Furthermore, if we expand that variance, the distribution becomes flatter, more spread. That's the orange line or yellow line. I don't know. Mustard? I don't know what that is. Anyway, and finally, we've got where we shift the mean slightly, right? We can shift the mean down 2 points. The mean shows up here for the green line. So once again, f of x gives the height of the curve or the relative frequency for any value of x with a mean mu and sigma, a variance sigma squared. So again, we can only compare within one distribution. If we were to talk about a height, let's say we have an observation at 0 and an observation at 1. On the blue distribution, the 0 is more likely than the 1. Actually, the 1 should be right here on the blue distribution. I don't know why I put it there at 0.75. Similarly, with the red, the 0 is more likely than the 1. If you look at the green distribution here, the 0 and the 1, still more likely, but it's harder and harder to tell, right? So this relative frequency, again, describes if we were to observe data like this, think of this curve as like a smooth histogram. It would sort of tell us where each of the data points are likely to fall. Likewise, we can plug in values in the normal distribution. Now, what you will note is because x shows up right here on the right-hand side, we have to calculate it for each value of x, right? So if we have a mean of 0 and a variance of 1, these top two lines are that normal distribution, and we wanted to compare the height of 0.5 to the height of 0.75, we plug in all these values at all the respective places on the PDF, and we get its result. We see that 0.5 gives us a value of 0.352, and 0.75 gives us a value of 0.301. So because 0.352 is higher, we'd say 0.5 is more likely if the mean were 0, the variance were 1, and this was normal. And you can see that here. The 0, 1 point is this red line. A 0.5 is right here, and that should be right about 0.352. And a 0.75 is like right here, which is just a little above 0.3. So you can see where those happen to be. So if you were thinking about where these curves come from, it's for plugging in all the values of x along the x-axis and calculating what the height of those happen to be on the y-axis, what the return value of the distribution would be. Now, we can go further. We can do this for any type of distribution. Like we could plug in a 0.5 into a distribution with a mean of 0, a variance of 5, and we get 0.079. And we can do the same thing. Now, we really can't compare and contrast this with the other two, right? Because it's sort of within a set of mean and variance. But this last one has the mean of -2 and a variance of 1. And we want to talk about which value is more likely, a -2 or a 0.75. We'll see -2 is, but this is another feature. The most likely value in the normal distribution is at its mean. So -2 is right at the mean of this distribution. So it will always be the most likely itself. And that doesn't mean you're going to observe it. That does not give it the probability that you're going to observe it. It just means relative to all the other values, it has the highest likelihood. Okay, so where did I get these numbers over here in this F? That comes, I actually used the Excel program, and if you type into a cell equals normdist, it'll ask you for the x, the mean, the variance, or the standard deviation, I believe it is, and it returns the value. If you're in R, which I would normally be in, you can actually use the denorm function and get these values too. Now let's talk chi-square. Now I put chi-square in here because it's not a distribution we tend to work with. It does show up from time to time. It's actually how we evaluate chi-square. Any statistics that follows a chi-square distribution, we use this to figure out its p-value. It's frequently used only in that sense. I don't know of statistics is a very broad field. Sure, people have used it as a distribution for data or in a model sense likewise, but for us, this is just to refer to it as another continuous distribution. The sampling distribution of the variance follows a chi-square distribution. So remember the sampling distribution from basic statistics. It's the distribution of the parameter if you keep doing the same experiment over and over and over again, getting the same with replacement for your data, taking successive samples from the same population. We also show that in maximum likelihood, the concept of a likelihood ratio test follows a chi-square distribution. Now, a likelihood ratio test is a model comparison between two models, one that is nested within the other, and it tells you you can use it to get the p-value for the parameters that you have to constrain to go from the nested model, or the full model, to the nested model. We're going to talk about that a lot more as we go forward. So for a continuous random variable x, the range or the support, the sample space is 0 to infinity. And that makes sense because if this is the distribution, the sampling distribution of the variance, so that's the scaled version of the chi-square, it's the sampling distribution of the variance. But yes, it's still chi-square is the core of it. That term right there, we know variances can't be negative. So yeah, that's where the bound of it happens to be. See, so this parameter matches the sample space. Hooray! Now, the chi-square distribution PDF is given by this ugly formula here. And if you're wondering, did I have this somewhere in my brain? No, I don't remember. I don't memorize this stuff. I look this stuff up. I don't expect you to remember it. There is one parameter in here's x, first of all, and then x is right here as well. And there's one parameter here, that is the Greek character nu. It looks like a V, so call it V, call it nu, doesn't make a difference to me. Now, this term, this hangman looking thing, is the capital Greek gamma, and it's called the gamma function, and it helps make the distribution itself integrate to 1. This is a really ugly and complicated function I won't go into. Just know it's there. Furthermore, with mathematical statistics, we can tell that that the parameter itself, the one parameter is actually the mean, the degrees of freedom, sometimes we call this parameter. And the variance of this distribution is actually 2 times the degrees of freedom. And why that happens? Calculus. And if you take in mathematical statistics class in a statistics department, you likely will end up having to demonstrate this as a part of the distributions class itself. No, we're not going to do that. We're just going to use it. I'm just using this to show you different continuous distributions. So here's a plot of chi-square. Again, its lower bound is 0. What you don't see is all the values leading up to positive infinity. And this plot, k really is our new parameter right here. Right? So this is the number of degrees of freedom, or you can think about that. You can see the shape of the chi-square with 1 degree of freedom, or one for a nu. It's this black line. It sort of increases up as you get close to 0. You'll note the mean of this is actually at its value right here. But here's the other kind of cool thing about chi-square. As these degrees of freedom increase, look at its shape, right? It goes from really going up, close to going almost infinite when you get to 0. And then it starts to look a little more bounded as you get to k equals 3. And then once you get to k equals 5, you're starting to see a shape over here that starts to look almost like a bell curve that's bounded below by 0. It's not there yet. But if you increase the degrees of freedom quite a bit, you'll start to see a shape that starts to look that way. Now let's talk about marginal, joint, and conditional distributions. These are types of distributions that we encounter in statistics. And occasionally you hear those words, so I want to define them for you as we go forward. So really, this is really important when we move from one to multiple random variables, right, in a multivariate setting. So when we have more than one random variable present, there's several ways of describing these different types of distribution. Right? Let's first consider the case where we might have 2 discrete random variables. Let's imagine I have a penny and a dime, and I want to record the outcome of the coin flip, heads or tails. Again, I'm not going to be the pro that lands it on its side, so just heads or tails for this one. And let's further imagine that the probability, remember this is the PMF, probability mass function, both of these are discrete distributions. The probability of a heads, or the result of the PMF, is 0.5. And the result of the tail for the penny is 0.5. And I just note head for penny is H sub P, tail for penny is T sub P. And let's say Z is the flip of the dime, heads for dime, tails for dime, HD, TD. And again, both of those is fair coin. It lands 50% of the time on each time. So we're going to talk about 3 different distributions. Use these to give us the context for describing 3 distributions. Now, I will note this context does apply to continuous distributions as well, but here, for our purposes, we are only describing it right now in discrete terms. It's a little bit easier to visualize, too. Okay, the 3 different ways that we can look at this is the marginal distribution, right? This is the distribution of one variable only, either f of x for the penny or f of z for the dime. Or we could talk about the joint distribution. For every flip, let's imagine I put the penny in the right hand, I put the dime in the left hand, and let's imagine I have the coordination to flip both at once. I do that. When they both land, I record what both of their values are. That would be f of x and z. That's our first look at a multivariate distribution. Sometimes we call that a joint distribution, right? That's the distribution of values for both x and z. Now, we know from a univariate distribution, a univariate distribution has a sample space. Well, it turns out a multivariate distribution has more than one sample space. It has a sample space of both x and z together. Finally, we could talk about the conditional distribution, right? This is the distribution of one variable conditional on values of the other. So again, let's think of that situation where I have right-hand penny, left-hand dime. I flip both at the same time. If I want to look at the distribution, the values of head conditional on, let's say, whenever I want to look at the values of the penny conditional on, let's say, a value of the dime. Let's say every time I rolled a head for dime, what were the values of the penny? That would be a conditional distribution, right? The conditional distribution of penny given a value of the dime. We could also look at the opposite conditional distribution. The values of the dime conditional on values of the penny, right? What are the values of dime every time I roll a head on the penny? Now, marginal distributions are exactly what we've worked with up to this point. We've seen continuous univariate distributions, uniform, normal, chi-square. We've seen categorical distributions just in the last slide, a flip of a penny, a flip of a dime. We get to joint distributions. This is where we represent the distribution of more than one variable simultaneously. Right? So this is representations of multiple variables. This is truly a multivariate idea. Right? So commonly, the joint distribution function is denoted with all random variables separated by commas. Right? So in our example, f of x comma z is the joint distribution of flipping of both a penny and a dime. Right? And as both are discrete, there are actually four possible values. Right? So it could either be f of head for penny, head for dime, f of head for penny, tail for dime, f of tail for penny, head for dime, and f of tail for penny, tail for dime. These are multivariate distributions. I keep saying that, try and drill that in. But we use joint distributions here to introduce two new important topics: joint distributions of independent variables. And in this case, my flipping of the penny and my flipping of the dime, in practice, you should not think that there's any different correlation here. I'm just literally flipping them both. So they're independent. And we'll also use this to introduce the idea of a joint likelihood. And this is really what's used in maximum likelihood estimation as we get further along. So joint distributions of random variables, of independent random variables, are pretty straightforward. Random variables are said to be independent. This is actually a statistical definition. Right? They are said to be independent, not mathematically speaking, but in the English way of thinking about it. They're independent if the occurrence of one makes it neither more or less probable of the other, right? So that means if I flip the head on the penny, I can still have a 0.5 chance of flipping a head or tails on the dime. Mathematically, we denote this as saying the joint distribution f of x and z is equal to the product of the marginal distributions, f of x times f of z. And in our example, flipping these are kind of independent. We can actually show this in a contingency table. So here's a contingency table. All four permutations of heads for penny, tails tails for both dime and penny are represented here. And what you'll end up seeing is that the margin of the table, that is where we look at just the probability of a penny. So this would be 0.5 and 0.5. The margin of the dime would be 0.5 and 0.5. And then for any given cell that's in the middle, that's our joint distribution. That's for here, this part that I'm wiggling the mouse over, that is the distribution where we'd say a head landed for penny, a head landed for tail. And because we know them to be independent, we can take the marginal, 0.5 for head for dime, and multiply it by the marginal, 0.5 for head for penny, and we get 0.25 in this spot. That same process works out. So should we do this experiment too long to count, trip over that needing a nap? flip it hundreds of thousands of times, what we should see is that we should see about 0.25 in each one of these cells and 0.5 on the margins. And this is what it should look like right there. So, but we can also marginalize across a joint distribution, right? So if you have now this is not just for independent distributions, not all, by the way, I should go back and talk a little bit about this. If these weren't independent, what we would see is that each cell would not be equal to the product of the margins. All right, that's the main thing. But in those situations, or even in the situation when whether or not it's independent, it sort of doesn't matter for marginalized. But if we had just the joint distribution, f of x and z, right? If we only had this center part of the distribution, how would we get to the external or the margin, the row or the column margin? We would use a process called marginalizing, right? We would marginalize across one dimension. So for categorical random variables, the word marginalize means sum across. So we go back here, the 0.2, we would get to the margin by summing 0.25 plus 0.25. That gives us 0.5. Mathematically, that is the sum character over the space of z. So the marginal distribution of x without z is simply the sum of the distribution PDF of the joint distribution over the values that z can take. So in our example, if we wanted the marginal distribution of a head on pennies, we would keep that notation-wise in place, but we would plug in what z can be. So that's heads or tails. And we flip back here, look at head for penny. Here's z for heads. Here's z for tails for dime. 0.25 plus 0.25 equals 0.5. So this is just the mathematical symbolic notation of what we just saw, adding up rows or columns in a table. And that works really nicely for categorical random variables. Turns out with continuous random variables, the sum doesn't really work, although depending on how much calculus you may have had, we know that an integral is like it's like a continuous sum. We are integrating across the space, so that marginal distribution of x, this little long snake-like swiggle-looking thing is the integral sign. This z says we're going to integrate across the z dimension. We plug in our joint distribution, and now this dz refers to which dimension it's over. It's the z side. So what ends up happening is either we sum or we integrate, but we end up with the distribution of x without z being involved. And again, this is what happens when you start with a joint distribution and you end up with margins. Now, this example, I've flipped it, right? We knew dimes and pennies and my coin flipping should be independent, so we just sort of took margins and built joint. More often than not, mathematically, we might have a joint distribution, like a multivariate normal distribution, and we need to show or even figure out what the marginal distribution for any one variable might be. Now, we're going to see in just a bit, as we go a little bit further, that multivariate normal distributions, each of the variables have a marginal distribution that's normal, but that's a later topic. Now, finally, there's conditional distributions, right? For two random variables, x and z, a conditional distribution is looking like this. The distribution of z given x, or flip of that, the distribution of x given z. The conditional distribution has a mathematical form where we take the joint distribution and divide it by the marginal that we'd like to condition upon. So f of z given x is the joint distribution of z and x divided by f of x. You could also think about what the distribution of x given z happens to be. And again, we start with that joint distribution right here. And now we're dividing by the marginal distribution of z. Now, conditional distributions turn out they are everywhere in the statistics. In fact, this thing right here starts to be the beginning of the classic Bayes theorem, which shows up in Bayesian estimation. We use conditional distributions for the general linear model as well, right? So if we were to create a regression line, so let's imagine this is x, this is y. It should be a y, it looks like an x right there. If we wanted to get the value of y for this value of x right there, there's our predicted value, but that turns out that's the mean of a normal distribution around it. That's supposed to be a bell curve, sorry for the sideways curve, but that should be its mean value. Now, we can also visualize conditional distributions with the contingency table. That would be like saying, what is the distribution of dime when penny equals a head? Right. So every time I rolled a heads on the pennies, this whole row right here would be the distribution of dime. Right. So that the probability of dime happens to be a head. Well, that look here, 0.25 and 0.25. Well, we can actually calculate it using the formula from before. The joint distribution is 0.25, the marginal distribution is 0.5, so this reweights it. Okay? So literally what we're seeing is that the distribution of a dime has a 0.5 for heads and tails when the penny is a head. Same thing with when the penny is a tail. Turns out that happens with independent distributions as well too. So we're going to show a conditional distribution with the linear model in a few slides, or you can flip back and see my terrible drawing with that. Let's talk about expected values and the algebra of expectations. All right, let's now talk about expected values and the algebra of expectations. Another word for expected value is simply a weighted mean based on the theoretical distribution, but we're going to get into how that works out. Expected values are statistics taken across the sample space of a random variable, right? They are weighted average. What are we talking about here? Right? So remember, mathematical statistics, we can do this without data. Right? So if you think about a random variable, it has a sample space. So let's say the coin flip, heads, tails. Right? Let's say this is a 0, this is a 1. Right? We have a probability mass function, looks like that right there. If we were to look at the expected value of this, not as a h plus t, but in terms of the numbers 0 or 1, what we would do is basically say, what is the average value weighted by how likely it were to be to occur, right? A 0 times 0.5 plus a 1 times 0.5. And that should equal just 0.5 itself. So the mean would be somewhere in the middle. So an expected value is a weighted average. What goes into it is the value from the sample space, and it's weighted by either the probability mass function or the probability density function. Right? Now, the notation that we use is this E function. So E represents an expectation, and in the middle is what we do to X. And when we just put X by itself, this is literally like taking the mean, right? But what we're going to see in just the slide is that we can actually take other statistics or other transformations of this and still apply the weighting function that we saw right here, weighting by probability mass, and we get things like variances or covariances. Right? Why I'm telling you this is that expected values allow us to understand what a statistical model implies about your data. Right? For instance, why is it that a general linear model specifies the conditional mean and variance for a dependent variable? And again, that would be like looking at this slide. For a given value of x, this is the conditional mean. I didn't describe what the conditional variance might be, but we could get that as well. So how we do this? In discrete random variables, because we use a sum, we take the value of the observation, x, we multiply it by its height of that bar chart in the probability mass function, and we sum that together across all the values of x. So this is nice and easy when we have a discrete random variable with a bounded sample. We don't have to do things like sequences or series to go and figure out the sum. So let's take an example from the roll of a die. A 6-sided die, right? A 1 occurs 1/6 the time. Again, this is a fair die, I should say. Each roll is equally likely, a discrete uniform distribution, if you will. Right? So we take the value that could be theoretically shown at the top of the die after rolling it, 1, 2, 3, 4, 5, 6. Each one of those has a probability of 1/6 of occurring. We put that all together and we'd say the expected die roll would be 3.5. Now, if you're like me and your children like to play Monopoly, you can talk about that. When you get close to, Park Place and Boardwalk, which one is more likely? How likely are you to land on Park Place or Boardwalk? That's a polite way of putting it. You may also think about this in playing craps at the casino, but again, that's a different class, a different topic, and that's not here for us today. For a continuous random variable, again, this sum is replaced by the integral. We don't like those things usually. They're a little bit more messy. And there, again, is the which dimension we're sort of integrating over. In this case, it's just x. But I will note that this is basically, if we look at that continuous distribution here, right? What we're doing, if you think of an integral, it's like taking a little tiny rectangle, infinitesimally small rectangle, weighting it. So what this is doing is taking each value of x that could possibly be, all the little ones, and weighting it by how much area would be in each of those rectangles there. Now, again, we're not going to calculate these with theoretical quantities. I just want you to see how this implies things about how models imply things about our data. Now, this is where things get really weird, right? If we, instead of x, if we plugged in x minus its mean, and then we squared it in this expectation function, we end up with the variance, right? Another way of writing that is x minus mu x squared, the expectation of x minus mu x squared. So this is a function of our data, or a function of, or a statistic, sometimes we might call this. Right? So for the roll of the dice, the variance, theoretical variance, is x minus its mean. Well, we just saw before it was 3.5 squared. So again, we weight each of the numbers, x, 1, 2, 3, 4, 5, 6. We're weighting it all by 1/6. And what we're plugging into the distribution here is the mean. And then we square it. And what we see is that the variance of the die roll is 2.92. And if we wanted the standard deviation, we just take the square root of that. And that means, on average, a die roll will land 1.71 dots away from its mean, the mean being 3.5. Similarly, if we have x and y, a pair of variables, the covariance is an expectation. Now, this is a little bit more complicated expectation. It's the expectation of the product of the variables minus the product of the expectations of the variables. Or another way of putting this, the expectation of the product. Now, in this case, we would have to, if the distributions were continuous, we'd have to do a double integral. Let's not go there. But you can see basically expectation continues throughout any type of distribution. And it's how you go and take a theoretical distribution and summarize its moments or its key parts of statistics, descriptive statistics. Okay, now we've come to linear combinations of random variables. A linear combination is a weighted sum. That's all you need to think about it. And you can think about something like beta 0 plus beta 1x. That looks like a regression line that happens to be a linear combination of a constant plus a constant times a variable x. A linear combination, again, is a expression constructed from a set of terms by multiplying each term by a constant and adding the results. This is a mathematical notation in general. A1 times nu 1, A2 times nu 1, all the way to AN times nu n. We see this a lot in multivariate statistics. We see this I just showed it to you in linear models, like linear regression. We might see this in the principal components analysis, where each of these is a weight, and each of these are the original values. We get to that later in a multivariate class. But more generally, linear combination of random variables have specific implications for the mean, variance, and even covariance of the new random variable or random variables, because covariance needs more than one. So as such, there are predictable ways in which the means, variances, covariances change, and that's what we call the algebra of expectation. And to guide us through this process, we're going to use descriptive statistics from a sample of people where we recorded their height, their weight, and gender as if male or female only. So in this case, we have a set of means. For the mean of the sample in this hypothetical example, 67.9. Height, the weight mean is 183.4, and half the sample would be female, consider female. We have a standard deviation and a variance for each. And in the table below, the bottom triangle of the table represents correlation between a pair of variables. So 0.798 is the correlation between height and weight. The diagonal of the table, this right here, are all the variances. And the upper triangle, these are covariances. And in previous classes, I've described a covariance right here as a rescaled version of correlation, or better yet, a value that has units attached to it, whereas correlation is unitless, meaning there's no inches or pounds or anything like that. It's literally just a number ranging between -1 and 1 for the Pearson correlation in continuous data. So here's some interesting parts about expected values and the algebra of expectation. Right? So these are true for any random variable, whether continuous, categorical, etc. And in this example, we're going to consider the symbol x and z to be random variables and the letters c and d to be constants. So if we talk about sums of constants, if we add a constant to every variable, right, what happens to the expected value of it? It turns out that is the expected value plus that constant. So it just shifts it. Think of it this way. If the height well, I'll show you this example in numbers in just a slide. For the variance, the constant doesn't shift at all, right? So the variance is something that doesn't change based on if we add a bunch of people. And you can think about this with like a normal distribution. Actually, I'll just show it right now, right? Here's the mean of a normal distribution, right? If I add to this the value c, what happens to my distribution, right? If this was, we call this 0, and the mean gets shifted to c, the whole distribution gets shifted over here, but the shape of the distribution or the variance itself is not changing. It's just where the center or the location of it happens to change. Similarly, with a covariance, if we add a constant to one or both of the variables, it doesn't change, right? Constants don't change the spread of the distribution. They just change where the mean is. Now, we get into products of constants. Let's imagine instead of adding a constant, we're multiplying it, right? So we take height and we multiply it by a constant like 2. What happens to the mean? Well, it turns out we pull that constant outside of the expected value function, and it turns out that constant multiplies the mean. Now, interestingly, for the variance, remember the expected value had a square term in it, so we actually take that constant square to multiply it by the variance. And in the covariance, if we multiply x by a constant c and d by a z by a constant d, we have to take both of those out of the covariance and multiply the covariance together. So putting this all together, if we have a sum of random variables, a weighted linear combination, we get c times x plus d times z. Then what we have is c times the expected value of x. The expected value of this new linear combination is the weighted sum of pulling out the constants and multiplying their expected values. And with the variance, this is where things get a little bit more interesting. We have c times x plus d times z. The new variance of that linear combination reflects c squared times the variance of x plus d squared times the variance of z, that is from this property. But we have an additional feature we have to worry about, which is 2 times those two constants, c times d, times the covariance itself. So this part right here makes making linear combinations of variables difficult in statistics. So we actually need to know that covariance term. So here's an example. Let's imagine we had weight in pounds and you wanted to change that to weight in kilograms. Turns out we can get a weight in kilograms by multiplying the weight in pounds by 0.453. So if we were to change our mean, if we were to report our data, but in kilograms, we could go back to our original mean of 183.4, multiply it by 0.453, and we end up with a mean in kilograms of 83.08 kilograms. Now the variance, similarly, the variance of kilograms, right, where we want to multiply weight by 0.453, we have to actually take that and square it and multiply by the original variance right here. And we end up with 652.38 kilograms squared. So that is our new weight in kilograms. Now the covariance of weight in kilograms with the height in inches, right? If we want to now covariate, what happens with just one? We're only multiplying 0.453 times weight, but we're leaving height the same. What we end up doing is pull out the one constant. We could actually think of this as the number 1 times height in inches, right? So, and that's the case, we get a new value where we see 0.453 times the old covariance gives us a covariance of 151.68 kilogram inches. And that's why covariance doesn't get used a lot, because it has units attached. But don't take my word for it. We can do this in R too, and you can see all of this works out the same. Here I have my data. Right here, I had the height in inches, I had the weight in pounds, I have the weight in kilograms. This is done earlier If I take the covariance value or I take the correlation value, you'll see the correlation doesn't change. Sort of remove the variance from it. These values are the same, but the covariance certainly change when we look at height in inches, weight in pounds. This is our original covariance. But when we switch to, actually this is variance, height in inches, weight in pounds, this is our original covariance. And this is our rescaled value from our previous slide right there. Now, it turns out when we do this in linear models, this happens a lot. So if you have a linear model, let's say with an interaction term, and you want to go and come up with a slope that's not present in the model itself by default, you have to make a linear combination. And in a previous class, I introduced you the multcomp package in R that uses something called the GHLT function. That does our linear combination. But we can think about it conceptually here, where we have a new random variable itself. Basically, we want to take the beta weight for, in this case, experience. This is the main effect or conditional main effect, and this would be a interaction term. If we wanted to and go and take 1 times each, we would come up with a brand new estimate of what a slope might be for a given value. And in that case, if we had a mean, the actual point estimate of the parameter is thought of as the mean, and the variance is the standard error squared. Right? So we have both of those. We get the standard error in output. We get the point estimate in output. So we have all of those, but what we don't have is this covariance. But it turns out that exists in the R object from the LM function. We just have to go and find it. Multcomp GLHT function does that for us. This is actually a SAS table. You can do this in SAS as well too. SAS actually uses an estimate statement in the proc GLM procedure. But this gives us each of those values. And again, what we have to think about is we have this weighted sum. The expected value is the sum times its constant. In this case, it's just this here. But the variance is includes this covariance term right there, 2 times it. So our new value of the variance happens to be 0.653. The square root of that is 0.257. And that gives us what we need to see to get our new estimate. Taking everything we've learned today, let's revisit the general linear model and see what the mathematical implications of everything are. Right? So let's imagine we have an outcome y that's continuous, a continuous random variable. And we're predicting it with a variable x, a variable z, and the product x times z. And I will note here we make no assumptions about x and z. These can be discrete, these can be continuous. They just exist. That is what we believe. They actually have to be random variables. They have to actually have some variation to them. Otherwise, it's just a constant. But that's all. Right? So y is the result of an intercept plus a slope times x, a slope times z, a slope times the interaction, and some random error. Now, in a linear model, general linear model, we make an assumption about error that it follows a normal distribution. It's actually independent and identically distributed from a normal distribution of the mean of 0 and some residual variance, sigma squared e. Y is dependent then on the linear combination of x, z, and e. This whole right-hand side is a linear combination using the terms from this lecture. The general linear model provides a model for the conditional distribution of the dependent variable y, where the conditioning variables are the independent variables, right? So what we're coming up with is a distribution of y given x and z. And the fact that they're given, they are constants. Now I've put constants in here. They're not really constants. Constants would just be one number. They are fixed, right? They're sort of just assumed to exist. The regression slopes, beta 0, beta 1, beta 2, beta 3, are also constants that are said to be fixed at their values. Later on, when in the context of sort of mixed models, we're going to contrast fixed effects with random effects, but for now we can call these fixed effects. So what does the GLM say about our data? Right? So we can use the algebra expectations in predicting y from x and z to figure out the mean. What's our mean y? Sometimes y hat. Well, that happens to come from the expected value of our regression line. And in this expected value, what we see here is we have a bunch of what we call constants, even though remember x and z are random variables, but they're just fixed. They don't follow a distribution that we're concerned about. So these terms all come out of the expectation right down here. Now, E is a random variable, but it has a mean of 0. Right? Error has a mean of 0, as we defined before. So we still need to leave it in the expectation, but because its mean is 0, when we plug in the expectation of it, it goes away, leaving us with the expected value of y conditional on x and z of being our regression line right there. Now, what's the variance? Well, again, remember what happens when we add a constant to a random variable in our algebra of expectations. So here, y by itself, we substitute the model for y. Again, all these terms right here don't vary. They're conditioned on. So they disappear, leaving us only with the variance of error, which is sigma squared error. And you'll note, this thing does not depend on x or z, meaning it is constant or homoscedastic. So when you hear the assumption, oh, linear regression assumes constant variance, yes, as a default it does, and there it happens to be. Now, side note, when we get to different ways of estimation other than least squares, we can actually turn that thing into a model as well too, and estimate it as well, where we can basically weaken the assumption of homoscedastic error variance. Now, what's the distribution of y? Right? So we just found the mean, the expected value, and the variance for the condition of the distribution of y given x and z. But what is the type of distribution? Right? So it turns out linear combinations of random variables that are normally distributed also result in random variables that are normally distributed. So because error follows a normal distribution, is the only random term in this GLM, the resulting conditional distribution of y is also normally distributed. So now we can go and show that y, the conditional distribution of y given x and z, is normal, where the mean of it is given by the regression line, and the variance is given by sigma squared error. Both of those things came from our previous slide. Right? So what does this mean in the context of data? Right? So if you recall the height weight data, we ended up predicting a person's weight in pounds based on their height in inches and whether or not they were female as an indicator variable, and the interaction right here. This is our regression line. We centered height at the mean, by the way, of 100 and, no, what was the height mean? 70 or 67 inches or something along those lines. So now this is our output from the analysis. And what we are going to show, this is the conditional distribution. If we were to plot y, these are different visuals from different web pages I've encountered in the past trying to teach regression. That's why when we look at this, we can see the shape of these normal distributions all follow along the regression line. The mean of this follows on the regression line, but the spread is identical across each. That's that idea, that assumption of homoscedasticity, where we only have one parameter for the variance. Similarly, if we treat our estimated values of the slope, we could actually go and talk about what's the predicted distribution for somebody who is given values of height or female, right? So a 62-inch female. Here we expect a 62-inch female to have a mean of 127.5. That's the linear combination. But we get the variance of that from this sigma squared error. And for a male or a non-female who is 76 inches tall, the mean weight would be 248.0 pounds with the same variance. But that's what we would end up getting. Now, I will note this is a little bit different. This is the mean. So what we would expect, because we're talking about the mean, this is the distribution of the mean of these folks. If we have a individual prediction, we have to go a little bit further. But this is where the idea comes from, mathematical statistics. And to emphasize the point that PDFs provide the height of the line, we can actually do this with the normal distribution as well. We plug all this in. That's how I plotted those distributions in the previous slide. This is where I got this shape to show up in R. Right there. Now that we've talked about how model assumptions work to build our general linear model, it is also important to talk about assessing how we evaluate whether normality is met. Now, you may have heard me say before that normality in a linear model is not about y, it's about error, and we'll talk about that in this as well, too. These methods, generally speaking, are not really that well used, but widely used, but they are possible to be used, and sometimes you may hear requests by reviewers or other people to go check the normality of residuals. and what you do. So this is intended to help with that. So the assumption of normally distributed residuals permeates the general linear model. But the good news about that is, of all the distributional assumptions, this seems to be the least damaging to violate. So that means these models are said to be robust to violations of normality, meaning if your residuals aren't quite normal, it doesn't change a whole lot of the results. So often this step is omitted. Depending on the context, depending on the field that you're in, some people will focus on it more. So I'll show it to you. There are methods that exist to examine residuals from analysis and then determine the adequacy of the model itself. And they come in different flavors. There's a graphical method using QQ or quantile plots. And then there is an actual hypothesis test, which is even more seldom used than the QQ plot approach. But actually, both of these have a few problems. The graphical methods that you show that you use don't determine how much of a deviation from normality is by chance. So you can't tell if this is normal. Like if you think about a sample of people, how frequently is it that these residual terms don't quite line up with normality? And hypothesis tests are actually the flip. They are overly sensitive to small deviations when the sample size is large. So they have really great power at detecting slight deviations from normality. Again, all of this adds up to say that this doesn't get used very much, but occasionally you will be asked to do so, oftentimes by reviewer two. Reviewer two, the one that always has a problem with your manuscript. So just in case, I'm going to show you how to do that. Now, I'm going to just add this to our lecture. This really tries to emphasize how distributions work. So we're going to briefly discuss both of these. Okay. So a useful tool to evaluate the plausibility of a distributional assumption graphically is something called a QQ plot, which is quantile versus quantile. So let's define what quantile is first. A quantile is the particular ordering of a given observation. So for example, imagine a person in our height data set with a height of 71 inches. They happen to be the 39th tallest person out of 50, right? That would correspond to, if you want to talk about percentile, they're at the 77th percentile of our distribution, right? Or they're taller than 77%. The QQ plot then takes that 77th percentile, turns it into what the raw value would be on a theoretical normal distribution, and compares the theoretical normal distribution with the observed data distribution. Turns out what you really want to see with this is if the data fall on a straight line when you compare the two. So here's an example. R actually has a built-in generic function named plot that if you take the result from your LM, so that model 5 is a linear model that we just shown with the main effect of height, main effect of female, and the interaction of the two. When you go and use plot on that, it will actually show you this normal QQ plot right here, where the theoretical quantiles, this comes from the normal distribution, where we took each person's residual and lined that up, found a percentile and mapped that percentile onto what the normal distribution should look like for it. And then we compared that to a standardized residual, standardized meaning the variance of these are set to 1. And what you should see, that dashed line going down the middle, is if everything was perfectly aligned with the normal distribution, they would fall directly on that line itself. Now, there are other plots in R, and I'm just going to skip those for right now. Those are there for other reasons. For example, this residual versus fitted value. This is trying to talk about any heteroscedasticity in the data that you might have. But anyway, normal QQ is what is an easy way to check your residuals. Here's an example of things that aren't so good. This is a normal QQ plot of credit card debt in thousands, right? So here this is the observed value, and this is our expected normal value. You can see credit card debt is bounded below at 0. The normal distribution is not. Furthermore, thankfully speaking, most credit card debt is relatively close to 0 on a basis, normal basis, right? Normal, not with the distribution, but on the bulk of this distribution is close to 0. And what that implies is that if we were to try to use a normal distribution with just pure credit card debt, it wouldn't fit. Now, again, credit card debt, if this were the outcome, we wouldn't necessarily need to worry about it being normally distributed. We need to worry about the residual, or what's left over after predicting it, being normal. So this is only applied to the E, or the error term, which shows up after you estimate your model. There was also a something called the Shapiro test, the Shapiro-Wilk normality test. So if we give it Model 5's residuals is a little piece of data that shows up in the LM object. We pass it to the Shapiro.test function, and it tells you with a certain p-value whether or not the data are normal. Now here, this is a significance test. The null hypothesis is that the data are normal. And if this p-value is very small, it rejects that null hypothesis, and you say it's not normal. But in practice, this test gives diverging information quite frequently. So if you are asked to evaluate the normality of residuals, the best way to do so is to consider both plots and tests, kind of converging evidence to say how it works. So wrapping up, this was an introduction to mathematical statistics to understand the implication of statistical models, the implications that statistical models make about your data. Although many of these topics don't seem to be directly relevant to what we're doing, they do help provide insights that untrained analysts may not easily attain. They also help you understand when and when not to use a model. Now let's talk about estimation methods. To talk about estimation, we're going to use a very small example data set. This came from Craig Ender's version 1 of his textbook about missing data, which came out in 2010. We're going to really only use 5 observations, really small data set, and that's to show the math behind the estimation calculations. So to set this up, the story described in the book, I think this is hypothetical data. Just imagine you're trying to hire employees for a job where an old-fashioned IQ score, like a Sanford Binet, would be important. So here, this employer, you're an employer, let's imagine. Let's imagine you collect 2 variables, IQ scores and job performance. So maybe they have a set of people who've already joined the company. They gave IQ tests to them. Here are the scores for IQ, and there's a job performance. It's on some type of metric going up to, 20 or something like that. You can see the descriptive statistics, the mean of each variable, the standard deviation of each variable, and here's your covariance matrix as well. It means the variance is down the diagonal and the covariance is in the off diagonal. So this is my big picture overview for how estimation works in a more or less sense. This is a gross simplification, but this is how I want you to think about it and how we'll talk about it throughout our versions of estimation that we go through. Most estimation routines do one of 3 things. First is they minimize something. And you typically find this with names that have least in the title. You may have heard about least squares in linear models. That is minimizing the squared distance between the predicted values and the actual data, or minimizing the squared residuals. Other versions of this include generalized least squares, ordinary least squares. That sounds kind of not the best name. Weighted least squares. I don't know if that's a good name either. Diagonally weighted. Ooh. And then weighted least squares, mean and variance transformation, or WLS&V. Oh, and if you really like it, iteratively reweighted. Anyway, this is often the estimator of last resort. It's also the estimator in many simple models where it does actually share point estimates with maximum likelihood. So turns out, even though this is the estimator of last resort, you're using it in linear models because it does correspond to point estimates that you would get for maximum likelihood in that one case. So that's one way estimation methods arrive at parameter values. Another way, another set of estimators maximize something, right? Something in this case might be a likelihood function, which I'll define as we go forward. Typically, this is found with names that have maximum in the title, and forms may include maximum likelihood, sometimes shortened to ML. You may see residual maximum likelihood or restricted maximum likelihood. That would show up in a mixed model. You may see robust maximum likelihood. That shows up in path analysis and structural equation modeling. And typically, because of the properties of maximum likelihood estimators, these are the gold standard of estimators. These are what people like to use the most. Finally, you might see other uses of estimation. We might use simulation to sample from something, right? In more recent advances in simulation use resampling techniques. Sometimes we call this Bayesian Markov chain Monte Carlo. You may have heard Gibbs sampling. You may hear Metropolis Hastings. You may hear the Metropolis algorithm. You may hear Hamiltonian Monte Carlo. That's a newer one. You may just hear Monte Carlo, depending on which type of science you're in. If you're in the hard sciences, Monte Carlo shows up. Now, often Bayesian methods are used for complex models where maximum likelihood may not be available, or for methods where prior information is needed for some of the parameters. So Bayesian statistics actually relies on a core that maximum likelihood does, which is a likelihood function. So let's introduce maximum likelihood estimation, shall we? Maximum likelihood, I mentioned just a second ago, that it is the gold standard of estimators. And the reason for that is the properties of maximum likelihood estimates. Now, I'm going to sound like a real statistician here, and I'm going to say, provided several assumptions, or better yet, what we call regularity conditions are met, and those are often met in data, I should say, maximum likelihood estimators have really nice statistical properties. One being asymptotic consistency, which means as your sample size increases, the estimator converges in probability to its true value. So that's a complicated jargony sentence. Let's unpack that for a bit. So as sample size increases, so you may hear this in the world of statistics, as n goes to infinity. This also gives rise to the idea of frequentist statistics. Basically, in the limit, what is the behavior of our estimator is what we're talking about. So as n goes to infinity, as we achieve, and sometimes when we get to infinity, now you may be like, wait, where is infinity? Turns out in statistics, infinity is still infinity, but for practical purposes, having a sample size that's not infinite, that's very large, basically is infinity. There's not a lot of difference between what a large sample might be and where infinity is. What a large sample is depends on the type of model. If you remember the t distribution in very basic statistics, it would describe it's described by one parameter, the degrees of freedom, just like the chi-square. Not a coincidence either. The t distribution as that degrees of freedom, if that were degrees of freedom were 1, 2, 3, something like that, it would not look. It would still be symmetric like normal, but it would have heavier tails. More of the observations would be extreme potentially. However, as that n goes up, once you get to about 25, or you have a degrees of freedom about 25, there's very little difference between a t distribution and a normal distribution. In fact, you can think of the normal distribution is the limit, or the asymptotic limit. As n goes to infinity, t essentially becomes normal. That's what we're talking about here. So that's the sample size idea. Now, converges in probability, meaning what happens is, as your sample size goes up to infinity, you can just imagine this, sample size increasing. That means the probability that you get the true values back for your model become 1. That's great. That's what you want to have. It's big supersized samples give you the right answers. That's a good thing. So that's asymptotic consistency. Asymptotic, again, is sample size increases, sometimes thought of as n going to infinity. And sometimes we even denote that as n with an arrow to infinity. So you may see that sometimes. Probably not if you're not into the theory side, but that's okay. The other thing happens in this is asymptotic normality. Right? As n goes to infinity, as your sample size increases, the distribution of the estimator is normal. And not only is it normal, we actually know sort of where its mean and variance are. Right? The normal distribution has 2 parameters. Right? And what am I talking about here? Right? So think of it this way. Your beta weights, your regression coefficients, those things don't have a distribution. But in frequentist statistics, we say, what's the behavior of them as n goes to infinity? Well, that turns out we can say, if n were infinity, these things would have a normal distribution, or as n gets larger, these things look more and more normal. And not only do they look more and more normal, the mean of that distribution is given by the point estimate of the maximum likelihood estimation process. And the variance of those is given by something called an information matrix, Fisher's information, which we don't really need to get into, but we know what it is. So why it's the case that we can say beta is fixed, and yet in your output from statistics, you can see a standard error for beta, is because we're implying that your n is large enough to use this approximate normality to go and figure out what the standard error should be. This also gives rise to hypothesis tests based on that standard error. And that's a very important feature as well. And finally, the last part of this is that maximum likelihood estimates are efficient, meaning no other estimator will have a smaller standard error. Again, standard error is the square root of this variance right here. Right? So what that means is you will get the best estimates, the most precise estimates that tend to be true as your sample size gets big. So that's why you may hear things like, oh, this is a large sample statistic or whatever. That really means, hey, we're using maximum likelihood and the properties of maximum likelihood are really, really nice. So because of that, because of these three, actually there's quite a few other properties, but these three in particular properties, maximum likelihood estimators are really commonly used in statistical estimation. So what goes into maximum likelihood? Well, maximum likelihood estimates come from statistical distributions, and those come from our model, and those are what assumed by our model. So we're going to begin today with a univariate normal distribution, but we're going to quickly move to other distributions as we go forward. So for a single random variable x, we saw the univariate normal distribution previously. This is its probability density function, or PDF. There's x. It has two parameters, the mean, mu, and the variance, sigma squared x. And previously, to plot a normal distribution, we'd say, oh, for a given at mu and a given sigma squared, once we plug in an x, we'll see how relatively likely that x is to occur, the height of the curve. Right? However, in estimation, we don't know what mu and sigma are, but we only know x. Well, it turns out the core of this function doesn't care, right? We just have a series of unknowns. So we have to build a little bit different version of this function, scale it up just slightly. But once we do, what we're going to see is we can use the same process to figure out how likely it is to see what a sigma squared is or a mu is in a normal distribution. So again, here's our univariate normal. Remember, this is given mu and sigma, right? So let's say mu is 0, sigma is 0.2, like in this blue line. For any given value of x, say x is 0, we can say the height of that curve is like about 0.9. And we can also say that at the mean, that's the most likely value and so forth that we see. It's more relatively frequent than other values. So here we are. This is putting it to place. Let's imagine we examine the distribution of IQ values for the values for an IQ variable, right? Let's assume that we know mu is 114.4, sigma squared is 5.29, and the standard deviation is the square root of it, or 2.3. Now, in reality, we don't know that, but I'm just showing you how we typically think of normal distribution, right? So what we do is, what is the likelihood or the height for the normal curve at 114.4? Well, we plug that into that PDF from a few slides back. And we see that 17.173. We could say the same thing. What's the likelihood of observing someone with an IQ of 110? And that happens to be 0.028. And so we'd say 114.4 is relatively more likely than 110. It's more close to the center of the distribution. We know all that. But what we don't know is the flip. If given a bunch of x's, we have no idea what sigma squared and mu is. That's what happens. That's what we have to build this maximum likelihood estimator. So what we're going to do is first build a likelihood function. A likelihood function provides a value of a likelihood, right? Again, think the height of a curve for a set of statistical parameters. Now, the likelihood functions are going to start with the same probability density function that you saw in the normal distribution already, right? But these density functions are provided for each observation individually. They are marginal functions. Our job then is to take these marginal functions and build them into something that's a joint function, a joint likelihood, a joint distribution. Joint distributions are technically multivariate, believe it or not. That's cool too. All right, so the likelihood function for the entire sample, not just a single observation. This slide's a single observation, right? This is a single observation of 114.4. This is a single observation of 110. We're talking about all the observations at once. So the likelihood function for the entire sample is the function that gets used in the estimation process. Right? The sample likelihood can be thought of as a joint distribution of all the observations simultaneously. So in univariate statistics, observations are considered independent, and we saw that before. Independent observations means we can form their joint distribution by product. So the joint likelihood function for the sample is constructed through a product. It's a product of each of the individual joint distributions. So let's look into that. Consider the likelihood function for one observation. Okay. So here's a one observation likelihood function. By the way, this is not tractable. This is not something we can use. You can't get a one-person sample. You can't get variance with one, and the mean is going to be very, very Otherwise, how shall I say, in hindsight, obvious once we get there. But yes, we have a one-person observation. Let's take the first person in our sample. It's 112. Let's also assume that the IQ follows a normal distribution. I don't know that it does, but we have to make that assumption to use the normal distribution function, the PDF for it. Let's also assume that the variance is known to be 5.29, right? All of this is to simplify the likelihood function so that we only don't know one value, right? We have to only have, there's only so much we can identify with one observation, but I'm going to try to show how this works. This is a feature we call empirical under-identification. With one person, we really can't estimate all the parameters of this distribution in a model. Right? We have to have a large enough sample to do so. Well, it turns out 5 is actually large enough to get estimates. They're not good estimates, but we could use it. All right, so for this one observation, the likelihood function takes its assumed distribution and uses the PDF. Right? This assumed distribution is normal. Here's your PDF. And so this PDF is now expressed in the terms of 3 unknowns that go into it, right? X, mu, and sigma squared, which is in 2 places. But because we know 2 of these terms, we know X, we know sigma squared, we can actually create the likelihood function for the mean. So how this is denoted is the PDF now switches the function formatting from an f of X to now a likelihood, and then on this side it's of mu. Now, X is considered constant and sigma squared is considered constant. So we know them. Right? We have to assume that to go into this. We just plug in their values in the respective places in the PDF, or now the likelihood function. So for every value of mu that can be, so what this function is giving us is for every value that we can plug into mu, it gives us a curve that talks about how likely it is that that mu is possible given our data and given our other parameters, right? So the actual value, just like in a PDF, the actual value of the likelihood is less relevant. It doesn't have a lot of meaning. It's all relative likelihood, but it's what we use to figure out what mean might be. Now, the value of mu that maximizes the curve, or that gives us the highest value, is called the maximum likelihood estimate. And there you have it. That's why it's called maximum likelihood. We're plugging in parameters that maximize the likelihood function, where the likelihood function involves our data. Potentially other parameters in the model, but usually just our data. So for one observation, what do you think that mean would be? If you didn't have this equation, if you were just sort of close your eyes to this thing right here, and you had one observation from a sample, and it was 112, what's the mean of that sample? Should be 112, right? So not really a sample, it's just a person, but the average of 1 is 1, right? It's sum of x over n. Sum of x is 112, n is 1, should be 1. There we go. So it should be 112. We should expect that. And we should see that when we do this calculation. So what this process is really doing, what maximum likelihood is doing, is saying, what's the most likely mean that produced these data? Right? Or put into the context of the linear model that you may know well about, what are the most likely beta weights that produce these data? So let's move forward. The value of mu that maximizes the likelihood function turns out to be 112. And this plot that you see right here is created by me taking this function in R, plugging in a range of values for mu of x just all along this x-axis, and calculating the height of the function. And you'll see the peak of that function happens to be right there. That happens to be 112 with a height of 0.173. So it should confirm what we already know about what a mean is. Now, that's one observation. Let's move to the sample itself. This is where things get a little bit more complicated notation-wise, and you should know I'll never ask you to actually form a likelihood function. I just want you to know where it's coming from. Because in the output of statistical models with maximum likelihood, you end up getting the log likelihood itself. Where does it come from? Let's find out. So we're going to make the assumption that our 5-person sample are independent and identically distributed. Because if they're independent, just like we saw in mathematical statistics, their distribution functions multiply. Now, a likelihood function is a type of distribution function, essentially. So for normal and distributions, this means the observations have the same mean and the same variance. They also have the same distribution PDF. Right? So if we plug this in mathematically, the likelihood function for both mu and sigma. Now, by the way, when we have a sample and we have more than 2 people, we can actually estimate those parameters. We have a sample of n observations. This is the likelihood of mean and sigma given our data, right? Well, if we break this down into one observation at a time, these are univariate normal PDFs that we're going to multiply. So it's the product of each of the PDFs. We plug the PDF in. And then this part down here is a step that has a little bit of algebra. And if you're rusty at algebra or maybe don't want to think algebraically, that's cool. I'll show it to you. We can actually simplify it to this function right here. So there we go. Once again, the multiplication comes from the independence assumption. Now, linear models that we've talked about up to this point all have independence assumption. The error terms have independence assumptions. But what if that doesn't happen? Turns out we have models for that. They're called mixed effects models. You may have heard of multi-level models, hierarchical linear models. Those are all models that sort of allow you to weaken the assumption of independence for certain units in your data. Now, from the previous slide, this was the function that we need to maximize, right? What do we know, right? We know what's in, let's just talk about what's in the function, right? There's a mean, a variance, and all of the data. Now, in our world, we collected the data, so we know X. We have no idea what the mean and the variance are, right? So this function, rather than providing the height of the curve for any value of X, it's actually providing the likelihood for any possible values of mu and sigma. So the goal of maximum likelihood is to find values of mu and sigma that maximize this function. And that then becomes a calculus problem. But we can play around without it. We can do what's called a grid search, for instance, right? So let's imagine we knew the variance was 5.29. Again, something we don't actually know, but this simplifies the process just a bit. It makes the search in one dimension, not two. Right? So we know the variance, but we don't know the mean. The likelihood function will give us a likelihood of a range of values of the mean, right? So here we plug in values of mu. We use our sample likelihood function. And what we end up seeing is, this is the shape. The peak of it happens at 114.4. And if you remember, that's our sample mean for IQ. So we still are, it turns out the mean is a maximum likelihood estimate for the normal distribution, sum of X over N. So we were actually using it without even knowing it. But this is where the mean is. The likelihood function's value is very, very tiny, 1.67 with 6, moving the decimal places 6 to the left. And we often denote this likelihood value as L to abbreviate it. Now, this is a really small number. And in computers, small numbers, well, there's always rounding error in computers, floating point numbers. But they especially get larger and larger the more data you have. This is with 5 observations. We had 500 observations, and we're multiplying together each of these PDFs. Remember, the PDFs are all decimal values. You would expect this likelihood number to get really, really tiny. We might exceed how small a number could get in our computer. So a way to change that is to take the log of the likelihood. So more often than not, we actually try to maximize the log likelihood function. Now you may be thinking to yourself, wait, that changes things. Well, yes, it does change things. It actually changes the scale of the y-axis by taking the log. It doesn't change the location where the maximum is, though. So even though we can take the log, right, we'll still find where the maximum is at 114.4, but now our likelihood function will just be a little bit different in terms of the value. So the log likelihood, we work through the math for this. We pass the log through all of the equations we did before. The log of a product of terms turns out to be a sum of the log of those terms, right? So then we can replace it to get the PDF, pass the log through, and we get this ugly looking function here, which I actually like better than the one before because we don't have Euler's constant involved in it. But that's just me. All right. So the log likelihood and the likelihood have have a maximum at the same location for both parameters here. So again, going back to our example, pardon my overlay problems here, but we know that the variance of X is 5.29, but we don't know what the mean of X happens to be. The log likelihood function will give us the likelihood of a range of possible values of mu. Right? So we just plug in, we try out mu values, And now this thing gives us the log likelihood. It's still the maximum at 114.4. But now the return value is negative 13.3, which is just the log of the return value of the likelihood before. And negative 13.3 is a little bit easier for the computer to work with. It doesn't have 6 zeros or 5 zeros leading it, which is what happened previously. But what about the variance? Up this point, we have assumed that sample variance was known, which is not likely to happen in practice. So instead, we can actually jointly estimate both the mean and the variance using the same log likelihood function. Now, the variance is just yet another parameter in the model. And so now instead of what we'll end up doing, let's see if my math will work here. Imagine this likelihood function is in 2 dimensions. There's trying out values of the mean, there's trying out values of the variance, and we might have log L as the z-axis. So you might end up having a bell type shape. And again, the overall global peak to that will be the location of the mean and the variance that maximizes. Those will be our point estimates. So the point to where the maximum is for mu and sigma turns out to be negative 10.7. You can't see it here, but the mean is still at 114.4. But sigma squared, this is really interesting. The estimate for it turned out to be 4.24. And so if you look at this plot, this is a surface plot. In the mean dimension, this is a nice curved line right here. But in the variance dimension, you can hardly see a curve. That's a very flat likelihood. And that reflects how hard it is to estimate the variance with only 5 observations. Now, what I've done is I've taken this surface plot in 3 dimensions and created what's called a contour plot. If I were to fly above the surface, so imagine flying right above it, these lines are equal height. They're like a contour plot like you'd see if you were hiking, right? Where different elevations are represented by different lines. Or sometimes in weather maps, they have contour plots for equal barometric pressure or equal temperature and so forth. But what you can see here is 114.4 is actually right at the peak, and 4.24 is right at the peak. So the center dot right here is the peak log likelihood. So going back to 4.24, I told you it was 5.29 on the previous slide, and it turns out that is the sample variance. Why is our MLE 4.24? Well, it turns out in maximum likelihood, the variance uses n in the denominator. It's biased. So our sample uses n minus 1. That is why. And with 5 observations, there's quite a big difference between our estimates. So the process of finding the values of mu and sigma that maximize the likelihood is quite complicated. And what I just showed you before was sort of a trial and error process. It was called a grid search. Basically, I plugged in values up to a certain precision of decimal places along both for mu and sigma squared. I actually, concentrated my search around where I thought they should be. Who would know what that is in practice, especially in complicated models with lots of data. And so this process that I just showed you was for didactic purposes, to teach you what's happening. In many cases, for models, and we would like to do is we can use calculus to find the maximum of the function itself. But the problem is, in a lot of complicated models, not all functions will have what are called closed form solutions, solutions that you can write down with an equation. We have to use an iterative process to figure out where the maximum is, a computational process. Right? But that process itself that we use is guided by something that we would call a really efficient process of searching for a parameter. One of those processes goes by the name of Newton-Raphson. So if you've ever taken a calculus class, you'll see this. It relies on derivatives in multiple dimensions of the likelihood function. So I will show you this briefly, but again, this is just to show you what's happening. The computer mostly isn't doing a grid search. It's using some type of calculus to optimize or to figure out what the maximum is. By the way, the maximum value is also sometimes called the optimal value if you're not in statistics. If you're in mathematics and or engineering, you're trying to find the maximum or the minimum of a function, that point is called an optimal value. But I digress. The calculus method to find the maximum of a function makes use of the first derivative, right? The first derivative is a function that tells you a line that's tangent to your curve at a given point. So when the first derivative is 0, that line's flat. That indicates we're either at a maximum or at a minimum. But it turns out our likelihood functions are inverted U-shaped. They look like that, sometimes called convex. So we know off the bat that if we find a first derivative that is flat like that, so 0 slope, that we found the maximum. If we had a U-shaped function, it might look like this. That's a minimum. And in general, if you take a calculus class, they will teach you methods on doing how to test whether you're a maximum or a minimum. We could do that, but all of our functions are going to be convex or inverted U's, so we know that they're going to be like this. And a flat line will be at the maximum. So here's a plot from Wikipedia of an example line. This is a tangent line. Each of those plot right there, that's a very complicated function, but you see where it goes flat. So in this part, it changes color at what we call local minima and local maximum, right? So each one of these parts is a sort of a part where the derivative changes direction, changes sign, right? Goes from a positive slope to a flat 0 slope to a negative slope, for instance. Our functions for most models are pretty well behaved. Sometimes you may have multiple peaks, but this is just an example of what the first derivative does in a tangent line. But we can actually use the calculus. I'm not going to make you, just bear with me here. If we use the first derivative, if we take the first partial derivative of the log likelihood with respect to the mean, and we do some algebra to it, what we can end up showing is that the MLE of a normal distribution for the mean is truly the sum of x over n, which is what we saw before. It's a great finding. Similarly, we could do the same thing for the variance. So we could use calculus, take the first partial derivative with respect to sigma squared, and now what we can end up finding is that the formula, we can find it, set that partial derivative equal to 0, do some algebra. We see this is the function for the variance that maximizes the log likelihood for all normal distributions. This happens to look like the variance formula that we used to call the population variance in simple basic statistics. I shouldn't say simple, I shouldn't say basic, but your very introductory statistics class, you may have heard of this as the population, and you'll see it's divided by n. That's where that comes from. Now, that's the point estimate. Let's talk a little bit about how we figure out the standard error. Turns out the second derivative describes the curvature at the point, at the maximum. And that is what goes into the information matrix. The information matrix, or Fisher's information matrix, named after the guy who gave us the F-test, Ronald Fisher, is found from the square root of -1 times the inverse matrix of second derivatives. And if you only have one parameter, it says one value, so it's not really a matrix. The second derivative gives the curvature of the log likelihood function, right? So that, for instance, if we take that log likelihood, start with our first derivative and differentiate a second time with respect to mu, so we start here, we can see that the variance of our mean is sigma squared over n. You've seen that before, right? If we take the square root of that, we are left with sigma x over the square root of n, also known as the sampling variance from the sampling distribution of the mean. Standard deviation, standard error of the mean. That's it. That's literally where it comes from. It's a maximum likelihood estimate. All right. Up to this point, we've played with numbers. Let's get into some statistics with software. There are packages in R that do linear models, but with maximum likelihood. Now, LS is not one of them. And why we'd use them, I will leave for a later discussion. But we can show them. For basic linear models, not something you necessarily have to do, but I'm just going to show you how it works. Nonlinear mixed effects or linear mixed effects 4 are two of them. You can see them other packages, like if you're in SAS, you can use procmix, you can use xtmix and stata. And I don't know the rest of them overall, but every package will have some type of maximum likelihood estimation system. These packages will grow in value to you as time goes on because most of multivariate analyses can be run with these programs, right? For instance, multi-level models, repeated measures models, some factor analysis models can run with them. Now, the mixed part of each of these, the M here, refers to mixed effects models. Those are models that feature fixed effects and random effects. The random effects are used to extend the linear model to allow dependency between observations, whether those observations are multiple observations from a person or within a group, or maybe even both. But that's not a subject for today's lecture. But let's just use this for our linear model that we've done before. Here, both packages use a common but very general log likelihood based on the GLM, and we had derived this previously, showing that if we had a model where we had a y being predicted by x, z, and its interaction, then the mean of the conditional distribution of y, what the model says the mean should be, is based on the fixed effects, and the variance is given by the residual variance. That in and of itself could then be, we could basically come up with a log likelihood for y based on this. And we could still do the same calculus to figure this out. There is a closed form, a set of equations for fixed effects. But this program doesn't necessarily find it. Actually, it technically does, but we're going to figure out it based on maximum likelihood. So the program here, actually, let me back up. There's a closed form. But it's a little more complicated. For any possible value of sigma squared, there's a closed form, but we don't know what sigma squared is. So what we have to do is use maximum likelihood to find sigma squared, and then use the closed form to figure out what the betas happen to be. And how it starts is the following. We have no idea what sigma squared is. So we start with a very naive guess. Hey, your sigma squared is 1. The end. Doesn't matter if your data is on the scale of thousands or decimals. 1. But that Newton-Raphson process figures out where the maximum is using ratios of differences in ratios of derivatives as it goes searching. So here's how Newton-Raphson works. We could calculate the likelihood over a wide range of values, like a grid search, but that is very difficult, and we have lives to live. So instead, what we're going to do is start with a guess. Right? So we start with a guess. We calculate the first derivative of the log likelihood with respect to sigma squared at that point. And if that first derivative equals 0, then we're done. But if it's not, if it's positive, we're too low. If it's negative, we're too high. So let's say we started over here, and we want to get to here. This is how it works. So what it first does is takes where we're at with our guess, right? And then we calculate the second derivative, right? And we use it to tell us how far off we are and to figure out how much to adjust by, right? So this second derivative will always be negative as we approach the top, but the first derivative can be positive or negative, right? So what we can show here is if the ratio of the first derivative to the second derivative is less than 0, we should guess a sigma squared that gets bigger. Or reverse of that, if it's greater than 0, we should guess a sigma squared that decreases. Or if it's equal to 0, we can stop. So that second derivative also tells you how good of a peak you are, how flat it happens to be, right? But that's a little bit later. We saw that earlier with the plot of the curvature around sigma squared. So NLME works very much like the nonlinear mixed effects function works very much, the package works very much like LM. We could even use the GLHT function from MultComp to do linear combinations of parameters. But what we're going to do is we're going to start with an empty model. We're going to predict IQ. We're not really predicting it, but just IQ for a person is equal to just simply an intercept plus error for a person. Because we know the point estimate of the intercept should be the mean, and we've already calculated that, 114.4. We also know that this should be about 4.24 if we're using maximum likelihood. So we should get those numbers back. So we're going to use the GLS function within NLME to do so. And then after that, we're going to replicate an analysis, or actually, it's not even replicate. We're going to predict performance from IQ. We're going to show how this works. What we're estimating is in this sigma squared error, and then the fixed effects fallout. So here is the GLS statement. We put IQ, our dependent variable, -1. That gives us just the intercept only. In our data set, we expect to have a variable named IQ. So data 01 should have a variable named IQ. And the only difference here is we put method equals ML, and that estimates maximum likelihood. So the summary says we're estimating by maximum likelihood. Turns out there is a log likelihood value that we see here, and it gives us 114.4 is our intercept, and we have our standard error there as well. Now, here are some of the names of the function that comes back. The key is that we have log likelihood. We have new interesting things called information criteria, a whole bunch of stuff that comes from it. But here's the basics of, I said proc-mix, that shouldn't be it, of NLME output. Here's all the objects inside that output. And what we see here is the number of subjects is 5, one variable or one parameter, and this is not residual maximum likelihood, which we're not going to talk about at the moment. Look, the other thing is, if you don't get results, you don't get convergence. Sometimes this may not find a maximum if you have some problems with your data. So if you don't get results, no numbers. But the nice thing is, if you don't, but the problem with convergence is this: if you don't have the convergence, all those good things, asymptotic consistency, asymptotic normality, all those don't apply to your results. So we want convergence. And we further unpack the output. In the summary function at the end, we see the residual standard error is 2.059126. If we square that, it turns out to be the same 4.24. That is the same sigma squared that we just found ourselves, right? It turns out, interestingly, you could actually get a standard error of sigma squared, although we don't actually see it in the output. You could get it using maximum likelihood. That is a big difference than you see from least squares. And finally, the information criteria, AIC, BIC. A stands for Akaike, the name of the person who created it. It's a Japanese last name, if I'm not mistaken. And B is the Bayesian information criteria, sometimes called Schwarz's criteria. These are numbers that involve the log likelihood and some other combination of how many parameters are in your model, and they potentially have what your sample size is. And what you end up doing is you can use these for model comparisons. Models don't have to be nested. Nested meaning that you can get from one model to the other by setting a series of constraints on parameters. So here, what we would end up doing if we had this model and we had a different model with a different set of predictors or however, we would compare the AIC across all models, and the one with the lowest value would be the preferred model. Likewise, we can compare the BIC across all models, and the model with the BIC is the lowest model. I'll just note, for a single model like this, there's no comparison. These are just values that you would use when you have more than one model to consider. And finally, the coefficients, also referred to as the fixed effects, are where the regression slopes are listed. And so here's the 114.4 for the intercept. That is the mean. And we also see that the standard error right here is 1.02. Again, that's 4.24 divided by the square root of 5. Or I guess the square root of 4.24 over 5. But what you don't see, though, if you ask for the ANOVA table, is an ANOVA table with mean squares, or sums of squares, mean squares, and F statistics. There is an F statistic here, but you do not see anything else. And that's because in maximum likelihood, the model itself, the process of likelihood estimation, is giving us sigma squared, whereas back in least squares, that mean square error was our point estimate of sigma squared. So that is different. As is, sometimes in least squares land, you could use the R squared change test. You may have read about that before. That is something we also don't use in ML to compare models. Okay, now let's talk about those useful properties of maximum likelihood estimates and how we can put them to use for us. Specifically, I don't know if these are properties or more like ways that we can calculate significance, but I will tell you that all of these apply regardless of whether we're using a linear model, could be a logistic regression, could be a path analysis, could be a structural equation model, could be a model that we haven't even invented yet. All of this still matters. So we're going to use likelihood ratio tests to make model comparisons when models are nested. We're going to use walled tests to look at specific hypothesis tests on single or individual parameters. You could also do walled tests for sets of parameters, but that's a little bit harder, so we're going to skip that part. And we'll look at those AIC, BIC information criteria to compare models as well. So to do so, we need another model. So let's consider our example where we wish to predict job performance from IQ, but now we're going to set our IQ at its mean of 114.4. So there's two models we're going to estimate. We're going to estimate job performance from an empty model, and they're going to predict job performance with IQ. And we're going to try to determine using maximum likelihood statistics which model fits better. So here is our model syntax. We put performance in the GLS function tilde1. This is for the empty model. We center our IQ, and we put performance tilde IQ 114. That is for the model with the prediction. And there are questions that we want to answer. Like, for instance, how do we test the hypothesis that IQ predicts performance? We can use a likelihood ratio test, that is comparing two models, or we can look at a Wald test for the parameter for the slope of IQ. Those are equivalent in this case, or asymptotically, as n goes to infinity, equivalent. So if IQ does significantly predict performance, what percentage of variance in performance does it account for? We're going to check for that also. So the first way to look at this, to compare two models together, is the likelihood ratio test. The likelihood value from the maximum likelihood estimate will help us statistically test competing models. That's that value that's at the top of the output. So a likelihood ratio test takes the ratio of likelihood for two models and use it as a test statistic. Now, remember, likelihoods aren't what we use. We typically use log likelihoods. So if you have the log of A over B, that is equivalent to the log of A minus the log of B from algebra. So what we're going to do is the difference between log likelihoods provides a likelihood ratio test. Sometimes this gets used the word deviance test. I like likelihood ratio tests. It applies all the time. But here, if we take the difference of our log likelihood, our null model, and our alternative model, the alternative model having more parameters, the null model having fewer. And again, these are for nested models, so we have to be able to somehow get from the alternative model to the null model by setting some equal to 0, for instance, but I'll show you that in just a bit. We take this difference, multiply it by -2. This term gets compared to a chi-square distribution, where the degrees of freedom is equal to the difference in the number of parameters. So let's put this to practice. All right? Let's imagine we wanted to test the null hypothesis that IQ did not predict job performance. Right? So we have a model. So basically, we're testing where beta 1 equals 0 against the null hypothesis where beta 1 is not 0. Now, we have two models. We have the empty model and the conditional model. There's only one parameter difference, right? The empty model does not have a slope, or beta 1 is equal to 0. And the conditional model is where beta 1 is not equal to 0. It's estimated, right? So we literally can get from the alternative model, or the conditional model, by setting beta 1 equal to 0, basically enforcing our null hypothesis. That means these models are nested, and we can use a likelihood ratio test. So here, the null model, we have one intercept and one residual variance, or two parameters. The alternative model, we have one intercept, one slope, and one residual variance, or three parameters. So the difference in log likelihoods times -2 will be compared with chi-square with 1 degree of freedom, which comes from the difference in number of parameters. So let's do that. Step 1, we estimate our null model. Here's our log likelihood. Step 2, we estimate our alternative model. Here's our log likelihood. We conform to calculate the distance, can't even speak anymore. Calculate the difference between log likelihoods. Multiply it by -2. We've got 14.4. And using the p chi-square function, we see the p-value with 1 degree of freedom is very, very small. Well, it turns out R will do this for us. The ANOVA function in R will allow it to happen. There's our likelihood ratio. There's our p-value. The test is model 1 versus model 2. And we would reject that null hypothesis in almost all circumstances, given that that p-value is really, really tiny. Pretty cool, huh? Now, likelihood ratio tests, again, work for linear models, but work for many other models as well. In fact, they work more frequently than they don't based on the models. There's a few models where you have to be a little bit careful with likelihood ratio tests. Those are the mixed models, but when we get to those, I will describe why and how to handle that. Now we have Wald tests. Wald tests are a different way of looking at it. Wald tests allow us to just estimate the alternative model, the model with all the parameters, and then parameter by parameter go and test those specifically, right? We know, for instance, our null hypothesis was that beta 1 equals 0, right? So really what we need to do is just look at the p-value for beta 1. Well, this is where that p-value comes from, right? So here If we take our point estimate of beta 1 against what we're comparing it to, in this case, that's 0, and we divide it by the standard error, which again comes out of the maximum likelihood estimate, this test can be compared to a z-distribution. Literally, that asymptotic normality assumption enables this test. So we can compare this with a standard normal distribution, right? So if we divide each parameter by its standard error, we can compute the two-tailed p-value from the standard normal distribution. There are a few exceptions if we have parameters with boundaries, variances, for instance. These are not recommended tests. But for all of the continuous parameters without boundaries, we could. And we can further add that variances are estimated, right? Switching this from a standard normal distribution to a t-distribution. R does this for this. Not all places do. Sometimes you'll see Z, like an M+, it'll have a Z over the title. And then sometimes, let's see if I can find an example here in R. Going way back. This is T value right here. But this T value is this 111 right here is 114.4 divided by 1.02. So point estimate divided by standard error. So what we're doing here, going back to our actual example, is we plug in the numbers, and we can see this p-value is 0.0058. Right? So our slope is 0.96. Our standard error is 0.13. We can take the ratio that gives us a statistic of 7.09 with a p-value of 0.0058 right there. So it's significant. So we reject that null hypothesis. So there we go. Finally, we can look at model comparison if we want to get an R-squared difference. We have to calculate the R-squared for both models. For the empty model, it's 4.16. For the conditional model, it's 0.234. Now, you might remember earlier in the lecture, the variance of IQ was 4.24. That's just a coincidence. 4.16, we're predicting performance for this, so it's a different variable. Right? But, here, the R-squared is 0.944, the difference between the two. So larger one minus smaller one over larger one says we've basically explained 94.4% of variance. I call that Hall of Fame worthy right there, which is awesome. Now, information criteria we could also use. I don't like to use these in nested models because the likelihood ratio test is the most powerful test. So it's much better at seeing this as best, but I'll just show you how these work. Here, for each model, we get an AIC and a BIC right here. So if we were to look at just the AIC column, which model has a lower AIC? Oh, look at that. Model 3A does the model with the slope. So we would prefer the model with the slope. The BIC is also, if we just look at BIC, right, just look at that, compare these two numbers. Oh, model 3 is preferred as well. Now, the problem with this is it's always the smallest value. Uncertainty isn't considered with this. So it's not like a p-value that goes with it. So it's a little bit different from the p-values that we see with likelihood ratio tests. But I do say the likelihood ratio test is the one to use unless you can't. So how do maximum likelihood and least squares estimation of the GLMs differ? Well, it turns out maximum likelihood and least squared estimates of the fixed effects are actually identical. Right? And for models with a single outcome where all observations are assumed independent, they will be identical. Right? Where they differ is in their estimate of the residual variance. In least squares, if we were to run this with the LM function, we would see the variance estimate to be, the residual variance to be 0.390, whereas in ML, it's 0.234, and that's because the ML version is a biased estimate. It's too small, right? And because sigma squared error plays a role in all standard errors, if this is biased, then we're more likely to reject those null hypotheses. And that won't be good either. Well, there is a fix. We'll see that later. And the hint of that is to use residual maximal likelihood, or to method equals REML, and that will be the fix. Hooray. So as we wrap up here, this was our first pass at maximum likelihood estimation. And I really believe in teaching this to you, even though it's a pretty technical topic, because most of the models that we get into in this class will be estimated using maximum likelihood. Now, again, maximum likelihood, what we saw here, likelihood ratio test, Wald test, information criteria apply to all statistical models estimated by maximum likelihood, not just linear models. And maximum likelihood estimation of linear models helps when basic assumptions are obviously violated, right? So where we might use maximum likelihood, where we might weaken the independence observation assumption, or we might use maximum likelihood to go and model the variance, right? Or we might have some problems with conditional normality of y. Our attention to Bayesian statistics. Much like maximum likelihood, Bayesian statistics involve a likelihood function. However, they augment the likelihood function with prior information about parameters. Bayesian statistics is used in a lot of advanced statistical methods, and so I feel it's important to introduce into this course so that we have an idea of what it might be, or that you have an idea of what it might be as you move forward, because it functions a little bit differently than any other estimation method that's out there. So, Bayesian statistical analysis refers to the use of models where some or all of the parameters are treated as random components. That means that each parameter comes from some type of distribution. The likelihood function of the data, like the thing that was being maximized in maximum likelihood, gets augmented with this additional term that represents the likelihood of a prior distribution for each parameter. The prior distribution reflects the belief an analyst might have about where or how certain they are a parameter might take a certain value. Right? This is like saying each parameter has a certain likelihood. And we saw previously that a likelihood is a height, is sort of a relative frequency. In this case, the likelihood is for a parameter, like the mean. How likely is it the mean falls between, let's say, 100 and 110? I'll show that in just a bit. The final estimates, the output of the Bayesian analysis, are considered summaries of the posterior distribution. So once you combine a likelihood with a prior distribution, using Bayes' theorem, you end up getting a posterior distribution. That posterior distribution is conditional on the data. So basically, we have a range of likelihood of where that parameter might be that reflects a blend of what the data tell us and what the prior belief happens to be. Now, in practice, we use these estimates to make inferences, just like we did when using non-Bayesian approaches to estimation, such as maximum likelihood or least squares. So why do people use Bayesian statistics? Well, Bayesian statistics typically get used because of the relative accessibility of one or more method of estimation. In our case, MCMC, which stands for Markov Chain Monte Carlo. Now, there are four main reasons I've seen people use Markov Chain Monte Carlo. Now, there may be more, but these are the four that I'm going to list. One is missing data. If you have missing data and missing observations in your data, Markov chain Monte Carlo is used to estimate the model parameters and impute the data. So in Markov chains themselves, it's relatively easy to make a very good guess as to what data might be using the rest of the data in your model itself. You can also incorporate very complicated models for certain types of missing data as you go forward. Now, another reason people have used Markov chain Monte Carlo is a lack of software capable of handling large size analyses with other estimation methods. So for instance, do you have a zero inflated negative binomial outcome or a binomial variable with 21 multivariate outcomes across 18 time points? Bayesian analyses are better for this because what ends up happening is in Bayesian software, you tend to be able to build a likelihood or build the component parts, likelihood and prior, much more readily than you can in self-contained other software like for maximum likelihood. Other reasons for using Bayesian include new models or generalizations of models that are not available in software, right? So if you have a new model, this is actually where I came to Bayesian statistics with. I was working in a field at the time called cognitive diagnosis. I like to call them diagnostic models now. This was early 2000s. At that time, we had no software to be able to what we did, so we actually had to turn to Bayesian. Because we could easily build it and incorporate it, plus we would know that it would be able to be estimated. So Bayesian provides lots of flexibility in crafting a model that fits the needs of your data more than other software packages that might be there. Now, those who are familiar with Advanced likelihood know that you could probably do the same in maximum likelihood sense as well. And there are certain packages that allow you to do that. So in SAS, for instance, there's the proc-NL mixed package for certain types of models, works very well in a general sense of estimating very complicated things with maximum likelihood, but it's still not as flexible as a lot of the Bayesian software that happens to be there. And then finally, I have to say this, Bayesians are kind of like a cult, and I'm a member of it, so that's fine. But there are philosophical differences that exist between numbers of the Bayesian analysis and other types of estimators as well. What a prior or posterior distribution actually reflects versus what we would look at as what we call an asymptotic distribution as n goes to infinity in maximum likelihood. So this cult of Bayes, if you will, cult of Bayesians love the ability to put prior information in. We say that, hey, this is sort of how the brain works. We take data coming in from stimulus, we take our prior beliefs, and we sort of blend them together to make a judgment about the situation. It's a relatively accessible system. Now, all that is to say that the use of Bayesian statistics has been very controversial. The use of certain prior distributions can produce results that are biased or that reflect subjective judgment rather than what the data is trying to tell you, objective science. So the use of prior distributions is a problem. There's subjectivity to it. And we can get into philosophical arguments as to whether subjectivity also shows up in maximum likelihood, in model choices, a lot of different ways subjectivity enters this. The nice thing about Bayesian statistics are if you're worried about the subjectivity of prior distributions, you can always try things with less sort of weak prior distributions that really don't put much impact on the data to see how much subjectivity is playing a role in your results. Additionally, most of the estimation methods are what we would call computationally intensive. In fact, until I would say the last 10, 15 years, very few methods were available for those who aren't into programming in Fortran, C, or C++. Now, there are packages and software programs that do a very good job with this, M+ being one of them. You'll see in R packages, there's the BRMS package that takes mixed models and puts them in Bayes fairly quickly. There are ways to make this easier, but it has been a kind of a challenging field. But some of us like the challenge, myself included. Furthermore, I think that widespread adoption of Bayesian statistics has been hampered by an understanding of how Bayesian methods work outside of the field of mathematical statistics. Now, this is certainly not the case now. For instance, there's a Bayesian software, a Markov chain Monte Carlo estimation method program named STAN. Actually, it does more than Markov chain Monte Carlo. Actually does maximum likelihood, does variational estimation as well too. It's a nice piece of software. It was heavily supported by Institute of Education Sciences and grant funding, and it's open source and free. So that Institute of Education Science really does fund educational work, and we have seen a move toward more Bayesian methods in education in the last 10, 15 years because of the work, in part because of people like those who developed STAN. So in the past 20 years, Bayesian methods have really become widespread, making new models more estimable and becoming standard in some social science fields, such as quantitative psychology or educational measurement. So let's talk about a little bit about how Bayesian methods work. I'm going backwards. There we go. So the term Bayesian itself refers to the Reverend Thomas Bayes, who lived in the 1700s in England. He formulated Bayes' theorem, and this right here is Bayes' theorem. The probability of event A given event B is equal to the probability of event B given event A times the probability of event A divided by the probability of event B. That's a mouthful. Now, if you remember from the mathematical statistics portion of the lecture, these are conditional and marginal distributions, right? This thing right here is a conditional distribution. And Bayes' theorem in many ways is a reorganization of how you go from a conditional or joint distribution to a marginal or conditional distribution, because you would see this part at the top. This is actually can be written as probability of A and B, the joint distribution of A and B itself. So Bayes' theorem is like a rewriting of the way distributions sort of work together. Now, each of these components, though, has a name. And in this case, here, this P of A, probability of event A, is the prior distribution, a PDF or PMF, of event A occurring. And then the way I'm talking about it and the way we talk about it in intro to statistics is like saying this is a discrete distribution, right? The probability that somebody has a rare disease is 0.01% in the population. That would be a prior distribution, but that is a discrete distribution. So we want to sometimes refer to that as a probability mass function, but PDF would still apply. That's on our names of it. But this is why things are Bayesian itself, right? This is something gets set by the analyst. We can decide what the prior probability happens to be. Now, P of B is the marginal distribution of the outcome, so sort of how the outcome occurs by itself. P of B given A is the conditional distribution of B given A. Now, this thing right here, we're going to come to see this is equivalent to our likelihood function when we get into statistical models. Now, discrete events like this example that you see on the slide here, it's a little less sure how we get there, but this is truly a likelihood function. In fact, it is identical to the likelihood function that shows up in maximum likelihood with different words to describe it. But finally, you put all these things, three parts together on the right-hand side of our equation here, and you end up with the probability of the event A occurring conditional on B. So in this case, this is the posterior distribution. This is what we're after, and this is how we build it. Okay, here's an example. Imagine the patient takes a test for a rare disease, some type of biological marker test. And let's say that rare disease is present in 1% of the population, but that the test has a 95% accuracy rate. What is the probability the patient actually has the disease? Before I do that, though, I did want to make a little bit of a sidebar. I'm such a member of the cult of Bayes that a few years ago I had the opportunity to take my children to London. And in London, we all got to pick something we wanted to go see. So my daughter, she wanted to see one of those old-fashioned English telephone booths, the red ones. They still exist somewhere, somehow. We found one of them, at least. My son, his name is Hugh. He wanted to go see Hugh Street, which is a street in the Chelsea neighborhood. Found him that. And for me, I picked a trip to go and see where Reverend Bayes is buried, and that is his tombstone right there in the middle of it. And it is in the Bunhill Fields Cemetery in London, off of, I believe it's called Old Street, if I'm not mistaken, but I may be wrong about that. Don't quote me on it, but you can find it and look it up. Other notable people buried there. You've got a few other notable people buried in the same plot of ground. So it is sort of an interesting historical place. I wanted to note a couple other things. This is also how you make your children very bored, because that's them right there. One's looking at a phone and the other one is saying, "Come on, Dad, do we really have to be here while you take your pictures of this old place?" But I thought it was important. So now if I ever get a grant that is notes, if I submit on a grant and they're like, "Oh, this project could use a Bayesian," I'm like, "Hey, I'm such a Bayesian. I went and took my kids to see Bayes' grave." All right. If you're ever in London, highly recommend. Oddly, there's not a line. There's no tourist attraction. You don't even have to pay money to get in. It's just right there. So highly recommend. Going back to our example, once again, let's talk about the patient with the rare disease. Now, let's let the letter D represent the case where the person actually has the disease. This is the hypothetical. And what we're really trying to decide is what's the probability a person has the disease given that their test was positive. So this plus right here is the positive for the disease. So here's what we know, right? Here's Bayes' theorem. If we put this into Bayes' theorem, so we're looking for the probability, the posterior probability of having the disease conditional on the test being positive. What we need to figure out is what's the probability of a positive test given they have the disease. That's what this term is. And then the prior probability of having the disease overall. So here, probability of having the test given that be positive given that they have disease, this is the accuracy rate of the test. It's 0.95. And we know from the story problem setup that 1% of the population has the disease. So that's the prior probability. So those are the numbers that go in the numerator. But the denominator takes a little bit more work, right? We actually have to go and think about this from what a marginal distribution actually happens to be. We can actually get the marginal by summing across the conditional. Remember, the marginal, if we have the probability of positive and disease, we could sum across the disease part of that and get to our marginal. That this now substitutes for this joint distribution, the sum then goes against the probability of the conditional positive given disease times the prior probability of disease itself. Now, this disease has two states. Someone can have the disease or not have the disease. That's where the sum takes its form over. So we know all these numbers, right? We know, for instance, the probability of positive given the disease, that's the accuracy, 0.95. The prior probability of disease, that's 0.01. That was part of the story problem. Then the converse of both of these, 1 minus that, shows up. So the probability of positive giving not disease, this would be a false positive, that's 0.05. And the probability a person doesn't have the disease in the population is 0.99. So when we do this sum of these two products, we get the number 0.059 that completes our denominator. And here's what we can answer. So if you are in the situation where a test is 95% accurate and there's a 1% chance that the disease exists in the population, the actual chance that you have the disease, given that the test is positive, is really only 0.17. There you have it. Pretty interesting stuff here. Okay. So that old-fashioned Bayes theorem example is something you might see in a textbook for introductory statistics. I found that to generalize the discrete nature of it to problems in modeling, right? So how does that relate to a linear model, a regression model? This is where I'm going to try to map it onto the regression framework a little bit more. Imagine you administer an IQ test to a sample of 50 people, right? Let's let YP be a person P's IQ test score. So if we were to put this into a linear models context, a linear model, an empty model for Y would look like this. We're going to say an IQ score is equal to an intercept plus error, where the error has some type of variance of it, right? So from this empty model, we know that beta 0 is the mean of Y. We've shown that in class already. And we know that sigma squared error is the sample variance of Y. Now, normally we'd call this residual variance, but here, because we're not predicting it with anything, it's not really residual. It's actually going to be the sample variance. So the distribution of Y, given those two parameters, is, when we derived this earlier, a normal distribution where the mean is beta 0 and the variance is sigma squared error. Okay. Now, up to this point in class, we've analyzed these data using maximum likelihood. I haven't gotten to REML yet, although I did talk about that, pardon me. But for maximum likelihood, we maximize the joint likelihood of the sample with respect to those two unknown parameters, right? So this is our maximum likelihood function, our likelihood function itself. This is not log likelihood, but we're going to get to log in just a bit, but we've seen how the relationship works between the two. So when we do that, we found that the log likelihood that maximizes the log of this function is negative 207.91. And here are our point estimates, 102.769 and 239.490. Now, to do this in a fully Bayesian approach would be to treat each parameter as being random, as a random instance from some prior distribution. So let's say we know that this version of the IQ test is supposed to have a mean of 100 and a standard deviation of 15. So that means if we believe that to be the case, our prior belief might be that the mean, or beta 0, should be 100, and sigma squared should be 225, which is really the standard deviation squared. So going a step further, let's say that you've seen the results for administrations of this test that led you to believe the mean came from some normal distribution with some standard deviation of 2.13. 2.13, that seems overly precise. Yeah, can be. But maybe that's the prior data that you had found. And so you're going to use that as sort of a guess for it. So that means we would have a prior belief that the mean should follow a normal distribution. Turns out our belief is bolstered by discovery of the central limit theorem that would suggest as n goes to infinity, the mean converges to a normal distribution, but that's neither here nor there. Let's just say it follows a normal distribution. The mean at 100, which is the mean that we know that the version of the test is supposed to have, and the standard or the variance of it being 2.13 squared, which is our observation maybe of a prior standard deviation from a sample put into the terms of the variances. All right, let's also say that you don't really have an idea as for the distribution of the variance, but you've seen it range between 200 and 400, right? So we're going to come up with a very naive prior distribution for the variance, a uniform distribution between 200 and 400. Now, normally we wouldn't want to do this. I'm doing this to avoid having to introduce you to some really ugly distributions that show up for variance. Not super ugly, but ugly enough to where I don't want to spend the time to distract us from this. But just note, I would never want to use a uniform distribution for variance. In practice, this is just for didactic purposes, right? Why not uniform? Well, first of all, why do we know it ranges between 200 and 400? And let me tell you, if you're going to make a job out of predicting variance, you're going to be out of work pretty quickly. It's very hard to predict what a variance in a sample will be ahead of time, ahead of collecting that sample, unless you know the population really well. Leaving that aside, a uniform distribution we know puts equal weight on all numbers between 200 and 400. So this allows me to introduce the concept of a uninformed prior, which means basically all values of variance between 200 and 400 are equally likely to occur in our prior belief. We really have no idea what's happening with variance, except for it should be between 200 and 400. All right, so putting this into Bayes' theorem, the Bayesian approach is to seek this posterior distribution of the parameters given the data. So we're looking for the posterior, the joint distribution of beta 0 and sigma squared given our data y. Right? These are the components of where we started with Bayes' theorem. So here A represents both these two parameters and B represents y for our data. So if we sort of mix them around or change them around using Bayes' theorem, what we can end up seeing is the following. We're looking for the distribution of what the data conditional on the parameters. Turns out this comes from our model. That's great. Times a prior distribution, joint distribution of beta 0 and sigma squared. And that's divided by this distribution of the data itself. If we look at this a little bit more thoroughly, what we just said in our previous slide is that we have a sense for what the prior for beta 0 should be and for sigma squared, but we don't have a sense of how they might covary together. They might be joint. So we're just going to leave them to be independent from a prior sense. Now, this being a prior distribution, that's fine. It's not really going to impact our results that much. So remember, a joint distribution is the product of its marginals if those marginals are independent. So we can separate that out here. And now we can remember that this distribution of beta 0 is normal. So we could use its likelihood function for it, normal likelihood. And the distribution of sigma squared error is uniform. And that uniform likelihood is also pretty easy to use. Now, what we end up doing is this f of y, that thing is kind of complicated. And so oftentimes, and it actually serves as what we call a normalizing constant to make the distribution sort of integrate to 1. So oftentimes we abbreviate this Bayes' theorem with this symbol. Looks like an infinity that got broken on one side, right? That means proportional to, right? So the prior distribution of these two parameters is proportional to, and this is where we put the things that support the numerator of Bayes' theorem in the proportional to side, right? Okay. So if we unpack it, here we go. This is the distribution of our data, conditional on the parameters. It turns out that that right there is our linear model. That's from our normal distribution, right? The mean of the normal distribution is beta 0. The variance was sigma squared e. We know that the beta 0 has a prior distribution with a mean of 100 and a variance of 2.13 squared. We can plug those into a normal distribution. So any beta 0 now gets a height, right? So every time we try a different beta 0 out, this is going to multiply the whole numerator of the proportional posterior distribution. And of course, the prior distribution for any value for the variance between 200 and 400 is the 1 over the upper limit minus the lower limit, or 1 over 200, or the number 0.005, which is the constant across each. All right, there's some more terminology. I would tell you that learning Bayesian is like learning yet another language in statistics, and here are some of the ways that we talk about it. The parameter of the model for the data the parameters of the model get prior distributions. But these prior distributions also have parameters, right? Here in the uniform, there's a lower upper point, endpoint, and a lower bound, upper bound and lower bound. Those distributions of the those parameters of the prior distributions are actually called hyperparameters. And yes, that is really their name, hyperparameters. Now, these are not estimated in our example, but there are cases where they may be estimated. If you're using a mixed effects model, for instance, the variance of random intercept is a hyperparameter that we're estimating from our data. So that is actually a case where we call that an empirical prior. Now, MCMC is our typical use of estimation, but we can show how estimation works in Bayes without having to use maximum likelihood. We just need to go get a plot of what's proportional to the posterior distribution. So we can do the similar grid search that we did previously in maximum likelihood to go and look at this, right? Again, in maximum likelihood, we tried values of the range, values of the parameter for a certain range, and tried to figure out where the peak might be, the maximum. Now that maximum, when we get to Bayes, is called a little bit differently. It's called maximum a posteriori, or the maximum or the mode of the posterior distribution. Maximum and mode, in this sense, mean the same thing. The mode of the distribution is sort of the most frequently occurring value. Well, it turns out the mode of a likelihood function is where the peak is, the maximum. Right? And sometimes we call this Bayesian modal estimation or MAP estimation. Now, in practice, this function is very similar to maximum likelihood, only instead of maximizing the joint likelihood of the data by itself, we just multiply that likelihood. That's our likelihood of the data. That's the same one we maximized in maximum likelihood. But now for every value of sigma squared right here and beta 0, we have to multiply it by their respective prior distribution heights, the likelihoods for each. And of course, we could use a log to make this work a little bit easier with the numbers. So if I just take the log of that thing, we can pass the log through, and now it's the sum of the log of each of the heights. So we're going to do that. So let's imagine again, to make it easy to plot this, that the variance is 239.490. This just allows me to plot in 2 dimensions instead of 3, which is a lot easier to show on slides. So we can actually use Excel or R to do a grid search over values of beta 0. Right? And for each value that we get, we're going to plug in that into our likelihood. Now, again, because we know sigma squared, I've taken that out of this equation itself. And as a comparison, I'll also search over just the maximum likelihood function as well, too, to find its peak. So here we go. This light blue line up here, that is our ML version. And this dark blue line is our Bayes version when we use a prior of the normal distribution with a mean of 100 and a standard deviation of 2.13. Now the peak, the maximum for under ML was right here, 102.8. But under Bayes, it was 101.4 right there. So what Bayes' prior is doing is 2 things. Number one, it's shifting the point of the maximum toward where the information of the prior happens to be. Right? We know that we put in the prior mean at 100, so it's shrunken what we saw in our data toward what the mean in the prior happens to be. But number 2, if you look at the curvature of the line for Bayes is much more curved. The prior is adding more information to where the peak might be. That's not information from your data, it's information from your prior belief. So what we end up seeing is that the standard error for this, what's sometimes called the posterior standard deviation, would likely be smaller than the standard error for the ML version. Now, what happens if we play around with the numbers a little bit? What if we increase our prior's variance to 1,000, right? Or standard deviation to 1,000, right? But here it was 2.13, and here it's 1,000. If you look now, the mean for each right here, these lines look almost parallel. The only difference is the actual resulting number is slightly lower. Right? This is what we call a non-informative prior. It puts very little information into the system. It doesn't change the result from ML very much. So if you're one that's a skeptic, and you should be, and you say, I don't believe that you can actually come up with a prior of 2.13 for the standard deviation. Come on now, that's, 0.13, that's oddly specific, right? Yes, it's oddly specific. So the alternative is try it with a very uninformative prior and see how much it changes. And in this case, it goes to 102.8. I will say that a lot of times, for the point estimates at least, uninformative Bayes priors give a mean or a mode of the posterior distribution at the point where our MLE might be. And one of the other things about Bayesian statistics is because the likelihood shows up, the likelihood that we use in ML shows up in Bayes, it still holds on to asymptotic properties like maximum likelihood does as well, meaning as n goes to infinity, we get the good stuff that ML gives. Asymptotic convergence, asymptotic consistency. It's really nice stuff. Now, here's what happens if you say, no, I really want a highly informative prior. Let's shrink that standard deviation to 0.15. Now, when that happens, our maximum for Bayes is right at the mean of the prior. So this would be like saying, hey, the data don't matter. And this is part of the controversy of Bayes. right? So in all Bayesian statistics, if you're reading people who are reporting Bayesian statistics, reporting the prior distribution choices is imperative because that's where subjectivity enters the analysis. And if a person were really wanted to do so, they could create a prior, sort of confirm their belief, almost as if they didn't have data in the first place. All right, this is what happens if we use another uniform distribution. Again, uniform between 1,000, -1,000 and +1,000. This is the definition of an uninformative prior. Again, it functions very similarly to that normal distribution with 1,000 for variance. So up to this point, in Bayesian statistics, what we've learned is parameters have prior distributions. That in estimation in Bayesian, this MAP approach, what I showed you in the previous slide, is much like estimation of maximum likelihood, only instead of the likelihood of the data, we now have to add in the likelihood of the prior for all of the parameters. Right? But again, just like we don't want to do a grid search in maximum likelihood, MAP estimation may be difficult as figuring out derivatives for the gradient function aren't always easy. Right? We could pick prior distributions that are great, really interesting distributions, but they may be very, very difficult to derive what the maximum might be if we wanted to use Newton-Raphson, for instance, or we wanted to calculate gradient functions to try to use Newton-Raphson to find a peak. There are a couple versions of priors that are a little bit easier to use. These are called conjugate priors. A conjugate prior is a prior distribution where the family it's from is the same as the posterior distribution. In our case, using a normal prior for this beta 0 is a conjugate prior. If we were to mathematically look at the form of a posterior distribution, the conjugate prior makes the math, the calculus behind it, go a lot easier. We don't need conjugate priors, though. We have lots of methods that go around them. And in fact, very few cases are really conjugate if you really want to have your full choice of prior distributions. And finally, prior distributions we've seen can be informative, meaning having a highly peaked likelihood function, or uninformative, like the uniform, a very flat likelihood function. And some uninformative priors will give MAP estimates where the point estimate is equal to that of ML. So basically, there's a connection of Bayesian to maximum likelihood. At the one extreme where there's absolutely uniform priors on everything, the peak of the distribution for MAP estimates mirrors ML. At another extreme, the data don't matter at all. You have these highly informative prior likelihood. And the reality is we tend to exist somewhere in the middle. Hopefully, I'm more on the side of do the least amount of subjectivity, but other people will disagree in certain places and in certain use cases. So next, let's talk about Markov chain Monte Carlo, where we can actually use a sampling approach for estimation. Markov chain Monte Carlo. This is the engine that drives most of what I do for Bayesian. Let's put it that way. I can't generalize to everybody, but for me, MC is what I use and when I use my Bayesian statistics. So let's review a little bit about how estimation works. Again, I mentioned this in the beginning of the lecture, but most estimation routines do one of three things: minimize something like least squares, maximize something like maximum likelihood. Markov chain Monte Carlo uses a different approach. It uses simulation to sample from the posterior distribution. And there are many named algorithms for MCMCs. They go by things like Gibbs sampling, Metropolis Hastings, Hamiltonian. There's a whole bunch of different ways that you can look at this. And then within each type of family, there are named algorithms. The Albert and Shib algorithm is a great one for Gibbs sampling in logistic regression, for instance, with what we call data augmentation. Long story short, what we're trying to do is use a bit of a brute force approach to figure out what the shape of the posterior distribution looks like. And if you're not in education or social sciences, if you're in the hard sciences, you might refer to these as Monte Carlo algorithms. And I mention that because the Metropolis algorithm, or Metropolis Hastings, dates to 1950 in computational chemistry. So this is an algorithm that goes way back. Wasn't really easy to be used until we got to where computers are widespread, not just widespread, but capable of doing complex processes in parallel, is really where we're at these days. So how MCMC works is basically takes samples from the posterior distribution of the data given the parameters. So again, we have this Bayes theorem thing to work with. And we don't know what that is, but that's okay. We're going to find out to work around that. So after enough values are taken, a rough shape of the distribution can be formed. We're literally talking about a smooth histogram of our summary of these sampled parameters. And from that shape, we simply take summaries from them. So again, the black box algorithm does its process. It spits back to you, let's say, 1,000 values for the mean should be. You make a histogram, a smooth histogram of it, and take the average. That's your mean. That's your point estimate of the parameter. You take the standard deviation of that. That's your posterior standard deviation. So how the sampling mechanism happens, it comes from several different algorithms like Metropolis Hastings or Gibbs itself. Gibbs sampling gets used where we know the posterior distribution. Those are where we have like conjugate priors, for instance. Not often a lot. Metropolis Hastings is more general. However, it is very inefficient. It basically tries random values from what we call a proposal distribution. It has nothing to do with your data or your priors sometimes. And basically, based on the weight of our proposed values versus our current values, we accept or reject. So we throw out a bunch of values. Later versions, like the ones using in STAN, use hybrid Monte Carlo, sometimes called Hamiltonian Monte Carlo. They use a Hamiltonian dynamics process from physics. Don't get me wrong. I am not the guy to describe that to you. But what it does is it makes it so that fewer of these proposed values get rejected. So it tries to sample in places that have more information. Right. So we're going to look at Metropolis Hastings within Gibbs. That is a very standard algorithm, very inefficient. It uses rejection sampling. But basically, we're looking to use it to go and get a posterior distribution for beta, 0, and for sigma squared. So we'll start both of those at some initial value. And they can be far from where the true value happens to be. We could start them at 0, or well, sigma squared has to be in the range of the parameter that's value possible. And we know that variances have to be positive. So, all right, we start a variance of 1, a mean of 0, call it good, see where it goes. That's fine. Then, for each step of the chain, for each one of the parameters, we draw a random value from what we call a proposal distribution. That's this Q function right here. All right. And we compare how likely it is our proposed value are. This is the numerator or base there right here for the proposed values versus how likely it is for our current values. And we weight that by how likely it is the proposed values got drawn versus, the current values got drawn. Flip the last two of those. So what we're doing is, we make this ratio, and given a random uniform number, if that uniform is less than R, we accept the new parameters. And if it's bigger than R, we reject them and just hold on to our current values. And this whole process, step 2 and 3, repeats for thousands of what we call iterations, thousands more samples. And that's sort of the magic. The magic of it is, actually, the statistical magic is, given data, a proper distribution for our data, we can even have improper distribution for our prior, and a few other things that tend to happen in data. The model's identifiable. We have no under identification in the posterior that we're forming. Given a long enough chain, our parameters will slowly move themselves around where their true values should be. Now, if you note that constant in the Bayes theorem algorithm, that thing would be the same for the numerator and the denominator of our Metropolis Hastings ratio. And if it's the same, it cancels. So we don't have to worry about it. Look at that. So the proposal distributions can literally be any statistical distribution. There is a little bit of an art to forming an algorithm with this. The trick is to pick ones that make the chain converge quickly. So interestingly, in software like STAN, or in another Bayesian software that's fairly widely used, just another Gibbs sampler, or JAGS. They'll do this for you. You don't have to build it. But if you're building it on your own, if you're building a custom one, there's a little bit of an art to it. You can find versions of this that are a little bit more efficient than others. These are ways of looking at it, but they literally could be anything, right? And given a long enough chain, the final values of the chain will come from the posterior distribution themselves, right? From that, you can get your parameter estimates. Here's what it looks like in JAGS. We basically say here's our data. Data follow normal distribution with some mean parameter and some, this is 1 over the variance. JAGS uses a weird precision versus variance parameterization, but we can get sigma squared right down here. We set prior distributions based on the normal and a uniform distribution, and then we let JAGs do its thing down here. I ran it for 50,000 samples for 2 different chains. Now, the chains themselves are sort of, let's start that whole process with a random initial value separately. The reason for that is we'd like to see that where our algorithm stops, what the posterior distribution looks like, is around the same area. It sort of gives us validity evidence that we're not somewhere stuck in a weird long distance place of our posterior far away from where the true value should be. So here is the output. These are sampled values of each of the means right here and each of the variances right there. And you can see each row is an iteration. Just disregard the deviance for right now. Tau is 1 over the variance. So if you were to take this number and reciprocate, but it's reciprocal as that right there. So you can see these are each of the values, and they're wiggling around. They're bouncing around. That's the way it should be. Here are what we call trace plots. On the left-hand side, this is each iteration starting at iteration 40,000 up to 50,000. Now you're like, wait, we ran 1 through 50. Why are you starting at 40? Well, everything before this part we call the burn-in, and we just omit it. That's the part where our parameter has to go from this random starting value to the center of the posterior distribution. So again, this is deviance, so I don't need to look at that really. These are the 2 parameters of entrance, mu and sigma squared. This is the value of each parameter at each iteration. And it's kind of hard to see, but there's 2 different colors overlaid on top of each other. There's the red and a black. The red is one chain, the black is a different chain. You wouldn't expect them to be perfect because this is a random process, right? In theory, both the red chain and the black chain ended up starting at randomly different places. So that's just going to be a different sample altogether. But you do want them to lie on top of each other so much so that it's kind of hard to see. That means they've converged at the same place. And then once we look at this, we kind of assess whether they converge. If they have, we pool all values, we forget which chain they came from, and we create a histogram, a smooth histogram, a density plot, if you will, of each of those parameters. Right? So the density for the mean, it looks nice and symmetric. And the central part of it is right about there. The variance is a little skewed, but we would expect that, particularly if we had a small sample. But we can see its uncertainty in the chain as well, too. So once again, the burn-in period is used where a chain is run for a set number of iterations before the sampled parameter values are then drawn and put into the posterior. Another thing that shows up in this approach is that because of the rejection and acceptance process, this rejection sampling, any 2 iterations are likely to have a high correlation. We call this an autocorrelation, right? So the correlation of a parameter value at iteration 1 will be potentially high between 1 and 2, right? One lag away. So what we often do is we thin the posterior chains, basically take every 5th or every 6th or whatever sample to reduce the autocorrelation. Really, the issue with autocorrelation is a high autocorrelation means we'll need a much longer chain to adequately sample the posterior distribution, and that the standard error of the posterior distribution may not be accurate unless we run that chain long enough. The other thing that we need to think about is chain length, right? How many iterations do we need? That also has to be long enough so that this acceptance rejection process can reasonably approximate the shape of this other distribution. And how do we pick these values? How many burn-in iterations, how many thinning iterations, how long the chain needs to be? Trial and error. That is the only way we can pick it. So output diagnostics is how we check whether we did it right. If we didn't do it right, we can go back and do it again with different values. Here are ways that we can check. We want that posterior time series plot to look like this. That looks good. Why I say that is, number 1, it's not trending in one direction or the other. And number 2, you see there's a lot of wiggle in between every different region. This one's not so good. It looks like we didn't let the chain run long enough because we started somewhere and it's trying to get down to where it finally converges. This is convergence. This right here would be burn-in, so we'd really want to cut that part off. This isn't great because if you look at this indicates a really high autocorrelation between parameter values. There's not a whole lot we can do to fix autocorrelation when it comes to model-based perspective, but what we'd have to do with this is run this an extra long time so that when we thin out, like let's say every 5th observation, we get a plot that looks like the one over here. And this last one, it's sort of a mix of both of those. It hasn't converged, and the values are highly autocorrelated. This is something where we'd want to look at whether our model is working correctly or whether or not we have some other problem with our identification of our model itself. Now, we actually can calculate, that's what we call the eyeball test right here. See if it looks like a nice caterpillar, like my students before like to call this a fuzzy caterpillar. We want a fuzzy one, not a little weak-looking caterpillar here. Maybe that's a smushed one. There are statistics for this. And one of the statistics that we often use is something called R hat, which is the potential scale reduction factor by Gelman and Rubin. Andrew Gelman, one of the most preeminent statisticians of our time, great Bayesian. Donald Rubin, also involved, another preeminent statistician. What we want, this right here, effectively looks at the ratio between chain variance to within chain variance. If that ratio is about the same, we know we have convergence. We want that to be 1. As a rule of thumb, 1.05 is sort of an upper bound these days. Earlier in the Bayes history, when early 2000s, it might be 1.1 people use, but 1.05 really is it. R hat is also why we want more than one chain run, because the more chains we get a better estimate of between chain variance, which helps us understand convergence. All right. Okay, so once again, this was our original distribution where we had a prior with our 2.13 as a standard deviation for the normal, mean of 0, a mean of 100, and then the uniform between 200 and 400 for the variance. Now let's change that up a little bit. If we had a very wide uniform for each, you can see these are the prior distributions for each. And this is the chain plots. And here is a more appropriate distribution for the prior. It's for the variance. It's a gamma distribution. You can see it changes values only subtly as well too. Here with a uniform, the variance of the posterior mean of the standard uniform is 244, and here it happens to be 253. And if we put a highly informative prior in, you can see this as well. It changes things as well, and our chain plots change accordingly. So if you want to do MCMC and R, this is just the beginning. I'm happy to point you to different materials on where to go. I've taught entire classes on this, particularly in psychometric models. But I start, of course, with linear models because I like those. There are other packages you can do this as well with. If you want Bayesian latent variable modeling, there is the Lavon package, but a Bayesian version of it by Ed Merkel. Blavon, that's a nice one. You can also run path analysis with an MCMC there as well. I'm not really showing, they can be buggy. Actually, buggy, they've gotten better, but setup is a little bit longer for both of these. It takes a few more things to install than you currently have. Well, that'll be it for Bayes today. It's an introduction to Bayes, just not even having you go and run analyses themselves, just to see how Bayesian works. But just remember, Bayesian statistics includes the use of prior distributions for parameters. We use 2 methods for estimation, MAP and MCMC. MAP is not very common, although it does exist occasionally in different software packages. MCMC is often used. Commonly, you'll hear people say Bayesian is MCMC, and that's not entirely correct. There are different ways of doing Bayes that are not MCMC based. But MCMC is an effective way of estimating most Bayesian models. And when you put this into code, what you need is to know the model data likelihood, right? That's your model, and your prior likelihood, and it will work, usually. But it can work very slowly because it is a brute force. We're basically sketching that posterior distribution. So that's it. Hope you enjoyed this lecture on estimation. That's it for me. Goodbye.